Hello there, and welcome to Just About Earth, the quiet corner where curiosity moves at an unhurried pace and the story of our planet unfolds gently, one idea at a time. This is a place for calm exploration, for drifting through deep time without rushing, and for letting science feel less like a lecture and more like a slow walk through an unfamiliar landscape. Tonight, we're going to travel farther back than most stories about Earth ever go. Not merely to the age of dinosaurs, or the first forests, or even the earliest animals, but to a time when the planet itself was still learning how to be a planet. A time before continents as we know them, before breathable air, before anything walked, crawled, or even stretched toward sunlight. Our destination is something called Vaalbara, believed to be the first supercontinent ever to form on Earth. Now, that word, supercontinent, might bring to mind Pangaea, the great landmass that existed hundreds of millions of years ago when dinosaurs roamed and the outlines of our modern continents were still taking shape. But Valbara existed unimaginably earlier, more than 3 billion years ago, so far back that even the rocks that remember it are rare and scattered, like fragments of a story written on pages that have mostly been erased. Trying to picture that world can feel a bit like trying to imagine your own home before it was built, before the street existed, before even the soil beneath it had settled. Everything familiar begins to fall away. The continents disappear, the air changes, even the length of a day is different. The Earth itself feels younger, more restless, still warm from its formation, still shifting and reshaping its surface in ways that would seem violent compared to the relatively stable world we know now. But before we drift further into that distant past, let me ask you something simple. Where are you listening from tonight? Maybe you are at home, wrapped in a blanket, listening through headphones while the rest of the room grows quiet. Perhaps you're in a different time zone altogether, somewhere the evening has only just begun, or somewhere the night is already deep and still. And what time is it for you right now? It feels fitting to ask because this story, more than most, is about time on a scale so vast that minutes and hours begin to feel very small indeed. If you find this kind of slow exploration soothing, if you enjoy letting your mind wander through the long history of our planet, I would be grateful if you considered liking the video or subscribing. It helps this quiet little space reach others who might appreciate a gentle journey through science before sleep. Now get comfortable, settle in, and let your thoughts slow down a little, because understanding Valbara means first learning to stretch the way we think about time itself. Most of us are used to thinking in years, maybe decades. History books might take us back a few thousand years to ancient cities and early civilizations. Geology pushes farther into millions of years, to the rise and fall of mountain ranges or the drifting of continents. But Valbara belongs to a time measured in billions of years, and that scale is difficult to grasp in any ordinary sense. One way to think about it is this. Imagine the entire history of Earth compressed into a single day, 24 hours from midnight to midnight. In that scale, dinosaurs would not appear until almost 11 o'clock at night. Humans, in their modern form, would arrive only in the last few seconds before midnight, and Valbara would exist in the very early hours of the morning, long before the world resembled anything we would recognise. At that time, the Earth was still young, less than a third of its current age. The surface was hotter, the crust was thinner, heat from the planet's formation and the decay of radioactive elements churned beneath the surface, driving intense volcanic activity. The continents, if they could even be called that yet, were small, scattered and unstable, forming and breaking apart again in cycles that lasted millions of years. And somewhere in that restless world, pieces of crust began to gather, slowly joining together into what may have been the first true supercontinent. The name Volbara comes from 2 regions where some of the oldest rocks on Earth are found: the Capval Craton in South Africa and the Pilbara Craton in Western Australia. Today, these places are separated by an entire ocean, thousands of kilometres apart. But when geologists study the rocks in these regions, they notice something intriguing. The ages of the rocks were similar. The mineral compositions matched in surprising ways. Even the patterns of ancient lava flows and sediment layers seemed to align, as if the pieces had once been connected. It was like finding two halves of a torn photograph on opposite sides of the world, and realizing they once formed a single image. From these clues, scientists began to piece together the idea that these Cratons, these ancient cores of continental crust, may once have been joined in a single landmass. Not a vast supercontinent like Pangaea, but something smaller, more primitive, the first step in a long sequence of continents assembling and breaking apart over billions of years. Imagining Vaalbara is not easy, because there are no maps, no clear coastlines preserved in stone, no forests or mountains in the sense we know them. The land would have been mostly barren rock, shaped by volcanoes and battered by meteorites that were still more common in those early times. The sky would not have been blue in the way we see it today. Oxygen was scarce, and the atmosphere likely held more carbon dioxide, methane, and other gases that would feel harsh and unfamiliar to breathe, if breathing had been possible at all. Yet despite these conditions, something extraordinary was already happening. Life had begun. Not plants or animals or anything large enough to see with the naked eye, but microscopic organisms living in the oceans, drawing energy from chemical reactions or sunlight, slowly beginning the long transformation of Earth's atmosphere and surface. These tiny forms of life would become some of the most important architects in the history of the planet, though at the time, their work was silent and invisible, carried out cell by cell in shallow waters. It is a quiet thought, really, to imagine that while the land was still raw and volcanic, while the continents were only just beginning to assemble, the first living systems were already at work, shaping the chemistry of the oceans, laying the groundwork for everything that would follow. If you picture the Earth at that time, it might help to imagine a world dominated by rock, water, and sky, with very little to soften the edges. No grass, no trees, no birds or insects. The wind would move across bare stone. Rain would fall on dark volcanic plains. The tides, driven by a closer moon, may have been stronger, surging across coastlines that were constantly changing, and the days themselves were shorter. 3 billion years ago, the Earth was spinning faster than it does now. A day may have lasted only about 18 hours. That means sunrise and sunset came more quickly. The rhythm of light and darkness cycling at a pace that would feel slightly hurried to us, though of course there was no one there to notice, no one counting the hours. It is strange to think about time passing on a planet with no clocks, no calendars, no living creatures aware of its passage. Time was measured only in cooling lava, in drifting plates of crust, in the slow accumulation of sediments on the ocean floor. And yet, those processes, slow as they were already shaping the future in ways that would echo billions of years later, all the way to the present moment, to you listening now. Another curious thing about Valbara is how little certainty there is. Unlike later supercontinents, whose outlines can be reconstructed with relative confidence, Valbara exists partly in the realm of careful inference. The rocks that remain are few, altered by heat and pressure over immense spans of time. Many have been recycled back into the mantle or eroded away. What scientists have are fragments, clues, hints, preserved in mineral grains and magnetic signatures frozen in ancient stone. Geology, in this sense, often feels like detective work conducted on a crime scene that has been rearranged repeatedly over billions of years, and yet, from these fragments, a picture begins to emerge. A world where the first stable continental crust was forming. A world where the processes that would later build mountains and shape oceans were already in motion. A world still very different from ours, but already recognisably Earth. Sometimes it helps to pause and consider just how remarkable that continuity is. The ground beneath your feet wherever you are is part of a planet that has been evolving for over 4.5 billion years. The atoms in the rocks, the minerals in the soil, the water in the oceans have all been part of this long story. passing through countless forms reshaped again and again. Vaalbara was not the beginning of Earth, but it was one of the earliest chapters in the story of continents, the first time large pieces of crust may have come together in a sustained way, forming something like a coherent landmass. And once that process began, it never really stopped. Continents would assemble and break apart repeatedly over geological time, forming and reforming in a slow cycle driven by the motion of tectonic plates. Valbara may have been the first, but it was not the last. Each supercontinent left its mark, influencing climate, ocean currents, and the evolution of life. Still, there is something especially intriguing about the first time it happened, the first gathering of land on a cooling planet, the first hints of a world beginning to organize itself into patterns that would repeat again and again. If you let your mind wander for a moment, you might imagine standing on a shoreline of that ancient continent. The air would feel heavy and unfamiliar. The sky might have a hazy reddish tint under a fainter sun, which itself was slightly dimmer in those distant ages. The ocean would stretch out before you, darker, perhaps tinged with dissolved minerals that gave it colours we rarely see today. There would be no sound of waves breaking on sandy beaches, because true sandy beaches were rare then. The coastlines were often rocky, shaped by lava and fractured crust. The sounds might be limited to wind, water, and the distant rumble of volcanic activity. It would feel lonely, but also strangely peaceful. A world still in its early stages before the noise of life grew loud. Trying to grasp how far back the world of Valbara lies requires a small shift in how we think about time, because the ordinary ways we measure it, days, years, even centuries, become almost meaningless when we stretch them across billions of years. Our minds are comfortable with the span of a lifetime, perhaps a few generations if we listen to stories passed down through families. History books might guide us through a few thousand years, and that already feels distant. But the age of Valbara belongs to a scale so vast that even the imagination has to slow down and take careful steps to follow it. A useful way to begin is to think about Earth itself. Our planet formed about 4.54 billion years ago. That number is easy to say, but difficult to feel. 4.5 billion years is not just a very long time. It is a length of time so immense that nearly everything familiar to us exists only at the very end of it. Mountains rise and erode, oceans open and close, entire ecosystems appear and vanish, and still the clock of geology continues ticking at its patient, unhurried pace. Valbara is thought to have existed more than 3 billion years ago during a period known as the Archaean Eon. That places it in a world that was already ancient by human standards, yet still relatively young in the life of the planet. The crust had formed, oceans were present, and the first life had begun, but almost everything else we associate with Earth today was still far in the future. One way to make sense of this is to compress Earth's history into a single calendar year. Imagine that January 1st marks the formation of the planet. For most of that year, life remains microscopic. Complex life does not appear until late November. Dinosaurs arrive around the middle of December and vanish on December 26th. Modern humans appear only in the last few minutes before midnight on December 31st. In that calendar, Valbara would belong somewhere around early spring, long before animals, forests, or even oxygen-rich air. Sitting with that idea for a moment can be strangely calming. It reminds us that the world we know is only a recent expression of a much longer story. The landscapes, climates, and living things around us are the result of processes that have been unfolding for billions of years, slowly and continuously, often in ways too gradual to notice in a single lifetime. Geologists have developed careful methods to measure these immense spans of time, because without such tools the deep past would remain forever vague. One of the most important of these methods is radiometric dating, which relies on the steady decay of radioactive elements within minerals. Certain atoms change into other atoms at known rates, like very slow hourglasses built into the structure of rocks themselves. When scientists examine ancient crystals, especially tiny durable minerals like zircon, They can measure the ratios of different elements and calculate how much time has passed since the crystal formed. Some zircons found on Earth are over 4 billion years old, survivors from a time when the planet was still cooling and solidifying. These minerals are not dramatic to look at. Many are smaller than a grain of sand, yet inside them is a record of time older than any mountain or ocean basin that exists today. It is a quiet reminder that the history of Earth is not written in a single book, but scattered in fragments, waiting patiently to be read. Thinking about such time spans can also change the way we think about change itself. In everyday life, change often feels quick. Seasons pass, buildings rise, technologies advance. But geological change operates on a rhythm so slow that it can feel almost motionless, like watching the hour hand of a clock. Only when we step back and look at the larger picture do we see how much has shifted. 3 billion years ago, the continents as we know them did not exist. The crust was thinner and more fragmented. Heat flowed more readily from the interior of the planet, driving frequent volcanic activity. The mantle beneath the crust was hotter, and tectonic plates may have moved more quickly, or behaved somewhat differently than they do now. Even the sun was slightly dimmer. This may sound surprising, but stars like our sun grow brighter over time as they slowly fuse hydrogen into helium in their cores. Early in Earth's history, sunlight was weaker, yet the planet was not frozen solid. Scientists believe higher levels of greenhouse gases in the atmosphere helped trap heat, keeping the oceans liquid despite the fainter sun. Pausing to picture that sky can be an interesting exercise. Without abundant oxygen, there would have been no protective ozone layer as we know it today. The colour of the sky may have been different, perhaps hazier, influenced by methane and other gases. Sunsets might have looked unfamiliar to modern eyes, their colours shaped by an atmosphere with a chemistry very different from our own. All of this was happening long before any human, or any animal, ever looked up and noticed the sky. There is something humbling about that thought. The planet has existed in countless forms, most of them never witnessed by eyes or recorded by minds. Entire eras passed in silence, marked only by the slow accumulation of sediments and the gradual reshaping of the crust. When we talk about Valbara, we are really talking about one moment in this long unfolding, a time when pieces of continental crust began to assemble into something larger and more stable. But even that assembly was not an event in the way we usually think of events. It was not a sudden collision or a dramatic instant. It was a process that may have taken tens of millions of years, perhaps longer, as fragments of crust drifted, collided and fused together. To the Earth, that was simply another slow step in its evolution. Another helpful comparison is to imagine walking a distance so long that individual footsteps become insignificant. Each step matters, but the journey is measured in miles, not in the motion of a single foot. Geological time works in a similar way. Individual eruptions, earthquakes, and sediment layers are like steps, while the formation of continents and the transformation of the atmosphere are like the long distances covered. Sometimes people ask why scientists are so interested in such distant times, periods so remote that they seem disconnected from the present. One answer is that the early Earth set the stage for everything that followed. The composition of the atmosphere, the structure of the crust, the chemistry of the oceans, all of these factors influenced the evolution of life and the development of the environments we now inhabit. Understanding Valbara is part of understanding how the Earth became a planet, capable of supporting forests, animals, and eventually us. There is also a quieter reason, one that has less to do with practical outcomes and more to do with curiosity. Humans have always been drawn to origins. We ask where rivers begin, how mountains form, how stars are born. Looking back to the earliest continents is simply another expression of that same curiosity, extended across a much greater span of time. The more we learn about these ancient periods, the more we realise how dynamic the planet has always been. Stability, in a geological sense, is often temporary. Continents assemble and break apart. Oceans open and close. Climates shift. ice ages come and go. The world we experience is one frame in a very long sequence. This perspective can be oddly reassuring. It reminds us that change is not an exception in Earth's history, but the rule. The landscapes around us, however permanent they may appear, are part of an ongoing process that began billions of years ago and will continue long after our own era has passed. Returning to the time of Vaalbara, it is worth considering just how unfamiliar the surface of the planet would have been. There were no soils in the modern sense, because soils are shaped by plant roots and microbial communities that did not yet exist in abundance on land. There were no forests to slow the wind or rivers shaded by vegetation. Rain fell on bare rock, and erosion carried minerals directly into the oceans. The oceans themselves may have looked different as well. Dissolved iron was more common in seawater, and in some regions this gave the water a darker or greener tint. Over time, microscopic organisms would begin releasing oxygen as a byproduct of photosynthesis, slowly changing the chemistry of the oceans and atmosphere. But during the age of Vaalbara, that transformation was only just beginning. Even the length of the year was slightly different in subtle ways. The moon was closer to Earth than it is today, and tidal forces were stronger. Tides may have surged farther inland in coastal regions, reshaping shorelines and mixing nutrients in shallow seas. These tides, driven by gravity and the steady motion of celestial bodies, were already part of the rhythm of the planet, long before anyone gave them names. Considering all of this together, it becomes clear that imagining the time of Vaalbara is not just about counting years. It is about reconstructing an entire world, one that operated under different conditions, yet followed the same physical laws that govern the planet today. The rocks that remain from that era are like messages carried across an immense distance. They tell us that continents were beginning to stabilize, that volcanic activity was widespread, that life was present in the oceans, and that the slow cycles of plate tectonics were already shaping the surface of the planet. Each discovery adds another small piece to the picture, though many details remain uncertain. The farther back we look, the fewer records survive and the more careful scientists must be in interpreting what they find. But even with these uncertainties, the broad outlines of the story are becoming clearer. Earth, in those distant ages, was not a quiet or static place. It was active, restless, and constantly changing. Heat flowed from the interior. Lava spread across the surface. Crust formed, fractured, and reassembled. Oceans circulated, and the earliest life quietly altered the chemistry of the world. All of this was unfolding long before the continents we know today had taken shape. If this was the first supercontinent, what exactly does that term mean, and how do pieces of a planet's crust gather together in the first place? Long before anything resembling a stable continent existed, the Earth was a very different place, a world still settling into itself, still shedding the heat and turbulence of its violent beginnings. To understand what the planet was like before land gathered into large recognizable masses such as Vaalbara, it helps to imagine Earth not as the calm blue sphere we see today, but as something far more restless, more molten, and far less predictable. The story begins even earlier than the Archaean, in a time when the Earth itself was still forming. About 4.54 billion years ago, our planet emerged from a swirling disk of gas, dust, and rock orbiting the young sun. Tiny particles collided and stuck together, forming larger bodies called planetesimals. These collided again and again, sometimes gently, sometimes with tremendous force, gradually building up the mass that would become Earth. Those collisions released enormous amounts of energy. Each impact generated heat, and as the growing planet accumulated more material, gravity compressed its interior, adding still more heat. Radioactive elements deep inside the forming Earth also contributed, releasing energy as they decayed. The result was a young world that was not merely warm, but in many places molten, with vast regions of magma churning beneath a primitive crust that formed and reformed repeatedly. If you could have seen the Earth during this time, it would have looked nothing like the familiar globe in textbooks. There were no oceans at first, no atmosphere in the modern sense, and certainly no continents. Instead, the surface may have resembled an immense volcanic landscape, glowing in places, dark and fractured in others, with lava seas stretching across wide areas. Over time, as the planet radiated heat into space, the outer layers began to cool. A crust formed, thin and fragile at first, often broken apart by new eruptions or impacts. Beneath it, the mantle remained hot and convective, slowly circulating like an immense sluggish current of rock. That circulation, driven by heat rising and cooling material sinking, would eventually become the engine of plate tectonics. But in those earliest ages, the process may have been more chaotic, less organised than it is today. The atmosphere of the young Earth also formed during this period, but not in the way one might expect. The first atmosphere, composed mostly of hydrogen and helium captured from the solar nebula, was likely stripped away by the solar wind, especially before the planet's magnetic field became strong enough to provide protection. What followed was a secondary atmosphere, built gradually through volcanic outgassing. Volcanoes released large amounts of water vapour, carbon dioxide, nitrogen, methane and other gases. There was little or no free oxygen. The air would have been thick, hazy and unfamiliar, perhaps tinted by volcanic particles and chemical reactions in the upper atmosphere. Sunlight filtering through this sky would have had a different quality, softer in some ways, dimmer in others. As water vapour accumulated, the surface cooled enough for condensation to begin. Rain fell, not for days or weeks, but perhaps for thousands of years in intermittent cycles, filling the lowest regions of the crust and forming the first oceans. These early oceans were not clear blue like those we know today. They likely contained large amounts of dissolved minerals, including iron, which gave the water a darker or greener appearance in some regions. It is quite interesting to think about the sound of that world, if one could have heard it. There would have been no birds, no insects, no rustling leaves. The dominant sounds would have been geological. The distant rumble of eruptions, the hiss of steam where lava met water, the crash of waves against raw volcanic rock. Thunderstorms may have been frequent, driven by a warm atmosphere and abundant moisture, lightning flashing across skies that no living creature yet watched. Even after oceans formed and the surface began to stabilise in places, continents did not appear immediately. Continental crust is different from oceanic crust. It is thicker, less dense, and composed of different minerals, and it takes time for such crust to develop. Early in Earth's history, most of the crust may have been more like modern oceanic crust, thin and prone to recycling back into the mantle. Gradually, through repeated cycles of melting, crystallization and differentiation, small fragments of more buoyant crust began to form. These fragments, known today as Cratons, are the ancient cores of continents. Some of them still exist, embedded within modern land masses, their rocks dating back billions of years. Before these fragments assembled into larger land masses like Vaalbara, they may have existed as isolated pieces, scattered across the surface like islands in a vast ocean. The spaces between them were filled with water, and the boundaries between crustal plates were sites of intense volcanic activity and frequent earthquakes. The heat flow from the interior of the Earth was also higher than it is today. This meant more vigorous mantle convection and likely faster rates of crust formation and destruction. The surface was in constant motion, reshaped again and again, with few places remaining stable for long periods. Meteorite impacts were more common as well. In the early history of the solar system, many leftover fragments from planet formation still orbited the Sun. Some of these collided with Earth, releasing tremendous energy and occasionally reshaping large areas of the surface. Over time, the frequency of such impacts decreased, but in the era before continents, they were still part of the planet's story. Another important difference in this young world was the length of the day. The Earth rotated more quickly then, completing one rotation in perhaps 14 to 18 hours during the earliest periods, gradually slowing over time due to tidal interactions with the moon. This meant that cycles of daylight and darkness were shorter, the sun rising and setting at a quicker pace than we experience now. The moon itself appeared larger in the sky because it orbited closer to Earth. Tides in the oceans were stronger, surging farther inland along coastlines and mixing the waters of shallow seas. These tides may have played an important role in the early development of life, concentrating chemicals and creating environments where complex reactions could occur. Life, in fact, had already begun by the time the first stable continental fragments were forming. The earliest evidence suggests that simple microorganisms existed at least 3.5 billion years ago, and possibly earlier. These organisms lived in the oceans, drawing energy from chemical reactions or from sunlight. They were small, simple, and extraordinarily resilient, capable of surviving in environments that would seem extreme by modern standards. Their presence, though invisible to the naked eye, began to change the planet in subtle ways. Some of these microorganisms released oxygen as a byproduct of photosynthesis, though it would take hundreds of millions of years for oxygen to accumulate in the atmosphere in significant amounts. At the time, most of it reacted with dissolved iron in the oceans, forming layers of iron-rich sediments that can still be seen in ancient rock formations today. Thinking about this period can feel a little like watching the opening scenes of a very long story, when the stage is still being set and the main characters have not yet appeared. The land is forming, the oceans are filling, the atmosphere is evolving, and the first living systems are quietly at work, preparing the conditions that will one day allow more complex life to emerge. The absence of continents as we know them does not mean the absence of land entirely. Volcanic islands may have risen above the oceans, some lasting for long periods, others sinking or eroding away. Chains of islands formed along plate boundaries, much like those in the Pacific Ocean today, though perhaps more numerous and more active. Rain and erosion began to wear down exposed rock, carrying sediments into the oceans. Over time, these sediments accumulated in layers, preserving a record of the environment in which they formed. These layers, compressed and transformed into rock, are among the clues geologists use to reconstruct the conditions of early Earth. It is remarkable that such records survive at all. Over billions of years, most of the crust has been recycled, melted or altered beyond recognition. Only a small fraction of the rocks from this era remain, and they are precious windows into a world otherwise lost to time. When we imagine the Earth before continents, it helps to let go of familiar landscapes and think instead in terms of processes. Heat rising from the interior, crust forming and breaking, rain falling, rivers carrying minerals to the sea, microorganisms growing in shallow waters. The planet was active, dynamic, and constantly changing, even if the changes were too slow to notice in a single moment. Eventually, some of those ancient fragments of crust began to collide and merge, forming larger and more stable landmasses. This process did not happen everywhere at once. It occurred gradually, over tens of millions of years, as plate motions brought fragments together. When enough of these pieces joined, they formed what we now recognise as the earliest supercontinent, Vaalbara. Understanding the young Earth before continents makes it easier to appreciate just how significant that assembly was. It marked a transition from a world dominated by scattered fragments and unstable crust, to one where larger, more coherent landmasses began to appear, influencing climate, ocean circulation, and the environments in which life evolved. When those early fragments of crust began to merge into larger, more stable landmasses, something new was taking shape on the surface of the planet, something that would repeat again and again across billions of years. To understand why Valbara matters, it helps to spend a little time exploring what scientists mean when they use the word supercontinent, because it is not simply a large continent, and it does not form in the quick or dramatic way our imagination sometimes suggests. A supercontinent is usually defined as a landmass made up of most or all of Earth's continental crust, assembled together in one place. That definition sounds straightforward, but the process behind it is slow, complex, and driven by forces so deep beneath the surface that we rarely notice them directly. The key to everything is plate tectonics, the long, steady movement of enormous slabs of the Earth's crust. The outer shell of our planet is not a single unbroken surface. Instead, it is divided into plates that float on the softer, slowly flowing mantle beneath them. These plates move at about the speed that fingernails grow, only a few centimeters each year, but over millions of years, that slow motion adds up to vast distances. At the boundaries between plates, several different things can happen. Plates can move apart, allowing magma to rise and create new crust. They can slide past each other, generating earthquakes. Or they can move toward one another, colliding in ways that reshape entire regions of the planet. It is this last type of motion, convergence, that plays the most important role in forming continents and eventually supercontinents. When two plates collide, one of them may be forced beneath the other in a process called subduction. The descending plate sinks into the mantle, melts, and helps generate volcanic activity, while the other plate may crumple and thicken, forming mountain ranges. Over long periods, fragments of crust can be welded together in these collision zones, gradually building larger and more stable continental masses. This is not a smooth or tidy process. It involves earthquakes, volcanic eruptions, and the slow deformation of rock under immense pressure. Yet from this constant reshaping, continents grow. Now, if we take a step back and imagine this process continuing over hundreds of millions of years, something interesting begins to happen. Continents do not remain isolated forever. The same forces that bring plates together in one region may pull them apart in another, but over time, there is a tendency for continental fragments to gather, forming larger and larger land masses. Eventually, enough pieces come together that a supercontinent forms. It might help to picture this in a very simple way. Imagine floating pieces of wood on a slowly moving surface of water. At first, the pieces drift separately, then currents push some of them together, forming clusters. If the currents continue to bring pieces toward the same area, the clusters grow larger until most of the wood is gathered in one region. That cluster would be like a supercontinent, though of course the real Earth is far more complex than floating wood. Once a supercontinent exists, it does not remain intact forever. The heat inside the Earth continues to move, and eventually stresses build within the crust. Rifts begin to form, cracks that widen over millions of years, allowing magma to rise and new ocean basins to open. Gradually the supercontinent breaks apart, its pieces drifting away from each other until they are once again scattered across the planet. This cycle of assembly and breakup is known as the supercontinent cycle, and it has happened multiple times in Earth's history. Vaalbara may have been the first example, followed much later by others such as Rodinia, Pannosia, and the well-known Pangaea. What is fascinating about this cycle is how long it takes. From the formation of one supercontinent to the formation of the next can take hundreds of millions of years. Entire mountain ranges rise and erode away in that span. Oceans open and close. Life evolves in ways that reshape the planet's surface. And yet, through all of this, the slow movement of plates continues, almost like a deep, steady rhythm beneath everything else. In the time before Valbara, the Earth's crust was likely more fragmented. Continental material existed, but it was scattered in smaller pieces. The mantle beneath the surface was hotter than it is today, which may have caused tectonic activity to occur somewhat differently. Some scientists think plates moved faster in the Archaean, while others suggest that plate tectonics was just beginning to settle into the patterns we recognise now. Either way, the formation of the first supercontinent marked an important transition. It meant that large portions of continental crust had become stable enough to persist and merge, rather than being continually broken apart or recycled back into the mantle. That stability mattered, because continents influence many aspects of the planet's systems. For example, Large land masses affect climate. They change wind patterns, alter ocean currents, and influence how heat is distributed around the globe. A supercontinent can create vast interior regions far from the moderating effects of the sea, leading to climates very different from those near coastlines. Continents also affect the chemistry of the oceans and atmosphere. Weathering of rocks on land releases minerals that are carried into the sea, influencing marine chemistry and, over long timescales, the balance of gases in the atmosphere. Even life itself is shaped by the arrangement of continents. The distribution of habitats, the isolation or connection of populations, and the availability of shallow coastal environments all depend, in part, on how land and sea are arranged. When we think about Vaalbara, we are looking at the earlier stage of this kind of planetary organisation, the first time large pieces of crust may have come together in a sustained way, influencing the environment on a global scale. Another important detail about supercontinents is that they are not always easy to recognise in the geological record, especially the older they are. Rocks are constantly being altered by heat, pressure, and erosion. Many of the oldest rocks on Earth have been transformed so thoroughly that their original features are difficult to interpret. To reconstruct ancient continents, geologists rely on several kinds of evidence. One of the most useful is the study of Cratons, the ancient stable cores of continents. These regions contain some of the oldest rocks on Earth, often more than 2 or 3 billion years old. By comparing the ages, compositions, and magnetic signatures of rocks from different cratons, scientists can sometimes determine whether those regions were once connected. Magnetic signatures are particularly valuable because when volcanic rocks cool, minerals within them align with Earth's magnetic field, preserving a record of the direction and latitude at which they formed. If two distant regions contain rocks of similar age with matching magnetic signatures and geological features, it suggests they may once have been part of the same landmass. This is one of the reasons scientists believe the Capval Craton in South Africa and the Pilbara Craton in Australia were once joined. Their rocks share striking similarities, and when reconstructed, their geological features appear to align in ways that are unlikely to be coincidental. Still, the picture is not perfectly clear. The farther back we look, the fewer clues remain, and the more cautious interpretations must be. Valbara is not mapped with the same confidence as later supercontinents, but the evidence is strong enough to suggest that something like it existed. It's interesting to think about how different that first supercontinent may have been from later ones. Pangaea, for example, was enormous, spanning nearly pole to pole and surrounded by a vast global ocean. Vaalbara, by contrast, was probably much smaller, more like a gathering of several large islands than a single massive landmass. Yet even a smaller supercontinent would have represented a significant change in the structure of the Earth's surface. Larger landmasses are more stable, more resistant to being subducted or broken apart quickly. They can persist for long periods, influencing climate and ocean circulation in ways that smaller fragments cannot. There is also something quietly remarkable about the persistence of continental crust itself. Much of the Earth's surface is constantly recycled. Oceanic crust, for instance, is rarely more than about 200 million years old, because it is continually created at mid-ocean ridges and destroyed at subduction zones. Continental crust, however, is more buoyant and resistant to subduction. Once it forms, it can survive for billions of years. Some of the rocks that were part of Valbara may still exist today, embedded within modern continents, their minerals preserving a record of a world that vanished long ago. Thinking about this can give a different sense of time. The ground beneath our feet is not merely old in a general sense. In some places, it contains fragments of crust that formed when the planet itself was still young, when the first supercontinent was assembling and life was only just beginning its long journey toward complexity. The formation of a supercontinent also changes the way the mantle flows beneath the surface. Large land masses act as insulating blankets, trapping heat and altering convection patterns. Over time, this buildup of heat can contribute to the eventual breakup of the supercontinent, as rising plumes of hot material weaken the crust from below. In this way, the formation of a supercontinent may contain the seeds of its own destruction. The same processes that bring continents together eventually help pull them apart again. It is a slow, patient cycle, unfolding over timescales so long that no single event defines it. Instead, it is a continuous process of gathering and dispersal, like a long, steady breathing of the planet's surface. Returning to the time of Vaalbara, it is likely that the world was still adjusting to this new stage in its development. The crust was stabilizing in places, forming larger land masses, while other regions remained active and fragmented. Volcanoes were common, oceans were rich in dissolved minerals, and the atmosphere was still very different from what we know today. And yet, even in that distant age, the fundamental processes that shape our world were already in motion. Plates were moving, crust was forming and colliding, heat was rising from the deep interior. The long cycle of continents assembling and breaking apart had begun, a cycle that continues to this day, slowly reshaping the map of the Earth. Understanding how supercontinents form helps us see Valbara not as an isolated curiosity, but as the first expression of a pattern that would repeat again and again across geological time. Reconstructing a continent that existed more than 3 billion years ago is not like reconstructing a dinosaur skeleton or mapping an ancient city buried beneath sand. There are no clear outlines preserved in stone, no coastlines waiting to be traced, no fossils of trees or animals marking the landscape. In fact, most of the crust that once formed that early world has long since been recycled, melted, buried, or altered beyond recognition. And yet, despite all of this, scientists have managed to piece together evidence suggesting that a landmass called Valbara once existed. The story of that discovery did not begin with a single dramatic finding. It unfolded slowly, across decades, as geologists studying some of the oldest rocks on Earth began to notice patterns that were difficult to explain in any other way. The key to the puzzle lies in Cratons, those ancient stable cores of continents that have survived since the Archaean eon. These regions are like time capsules preserving rocks that formed billions of years ago. While much of the Earth's surface has been reshaped repeatedly, Cratons have remained relatively stable, allowing ancient geological records to endure. Two of the most important Cratons in this story are the Capval Craton in southern Africa and the Pilbara Craton in Western Australia. At first glance, these places could hardly seem farther apart. They lie on different continents separated by vast oceans and surrounded by landscapes shaped by entirely different climates and histories. But when geologists began examining the rocks in these regions more closely, they noticed something intriguing. The ages of many rock formations in both Cratons were remarkably similar, dating back more than 3 billion years. That alone was not enough to prove a connection, since ancient rocks exist in several parts of the world. What caught scientists' attention was the similarity in the types of rocks, the sequences in which they appeared, and the geological structures they contained. It was as if two distant libraries held fragments of the same long-lost manuscript, written in the same style, using the same materials, and arranged in the same order. To understand why this was significant, it helps to think about how rocks form. Different environments produce different kinds of rocks. Volcanic eruptions create lava flows and ash deposits. Shallow seas produce sedimentary layers rich in minerals carried by rivers. Deep burial and heat transform rocks into metamorphic forms with distinctive textures and compositions. When geologists examine ancient rock sequences, they're essentially reading a record of environments that existed long ago. If two distant regions show matching sequences of rocks, formed at the same times and under similar conditions, it raises the possibility that those regions were once part of the same environment. But geology alone was not the only clue. Another line of evidence came from paleomagnetism. the study of magnetic signatures preserved in rocks. When volcanic rocks cool, tiny mineral grains within them align with the Earth's magnetic field, recording the direction and inclination of that field at the time the rock formed. By measuring these signatures, scientists can estimate the latitude at which the rocks originally formed. If two regions contain rocks of the same age with matching magnetic signatures, it suggests they were located at similar latitudes when those rocks formed. In the case of the Vaalbara and Pilbara Cratons, paleomagnetic data indicated that they may once have been positioned near each other. Of course, matching latitudes alone would not prove a direct connection. Continents can share similar latitudes without touching. But when paleomagnetic evidence is combined with similarities in rock sequences, mineral compositions, and geological structures, the case becomes stronger. Gradually, a picture began to emerge. Some scientists propose that these two cratons were once joined, forming part of a single landmass that existed more than 3 billion years ago. They gave this hypothetical continent a name derived from the regions that preserved its remnants, Vaalbara, combining Vaal and Pilbara. It is worth pausing to appreciate how tentative such reconstructions must be. Unlike later supercontinents, whose outlines can be traced through multiple lines of evidence across many continents, Valbara is known from only a few surviving fragments. The farther back we look, the fewer clues remain, and the more careful scientists must be in drawing conclusions. Even today, there is ongoing debate about the details. Some researchers suggest Valbara was smaller or more fragmented than originally proposed. Others question whether all the evidence points to a single coherent landmass or to several loosely connected regions. Science, especially when dealing with such ancient times, often progresses through careful disagreement as much as through consensus. What remains clear, however, is that the similarities between these ancient cratons are too striking to ignore. They suggest that large pieces of continental crust were already forming and interacting billions of years ago, marking an important stage in the evolution of the planet's surface. Another fascinating aspect of this discovery is the way modern technology has helped reveal clues hidden in rocks that have endured unimaginable spans of time. Advances in radiometric dating, for example, allow scientists to determine the ages of rocks with remarkable precision. Tiny crystals within the rocks, sometimes smaller than grains of sand, contain isotopes that act like microscopic clocks, ticking steadily over billions of years. By analysing these isotopes, geologists can reconstruct timelines of volcanic eruptions, sediment deposition, and metamorphic events. When timelines from different regions align, they provide another hint that those regions shared a common geological history. Geochemical analysis has also played a role. Rocks contain trace elements and isotopic signatures that reflect the conditions under which they formed. Comparing these signatures across distant cratons can reveal surprising connections, suggesting that the rocks originated from similar magmatic sources or formed in similar tectonic settings. In a sense, scientists are not just studying rocks, they're studying patterns, looking for echoes of ancient processes preserved in mineral structures and chemical ratios. There is something quietly remarkable about the patience required for this kind of work. Discoveries about Valbara did not come from a single expedition or a dramatic moment in the field. They emerged gradually as researchers compared data, re-examined samples, and refined their interpretations over many years. It is a reminder that science often advances not through sudden revelations, but through careful accumulation of evidence piece by piece until a pattern becomes visible. Imagining the disappearance of Valbara can also help explain why its traces are so scarce. Over billions of years, the surface of the Earth is constantly being reshaped. Erosion wears down mountains and carries sediments into the sea. Tectonic forces push rocks deep into the crust, where heat and pressure transform them. Subduction carries oceanic crust back into the mantle, where it melts and is recycled. Even continental crust, though more resistant, is not immune to these processes. Parts of ancient continents are broken apart, buried, or altered beyond recognition. What survives is often only a fragment, preserved by chance in regions that remained stable long enough to escape destruction. This is why Cratons are so important. They are among the few places where rocks older than 3 billion years are still exposed at the surface. Without them, the story of early Earth would be almost entirely lost. Standing on one of these ancient Cratons today, it is difficult to imagine the world in which those rocks formed. The landscapes around them have changed countless times. Mountains have risen and eroded away. Oceans have come and gone. Yet beneath your feet may lie rocks that were already ancient when multicellular life first appeared. It gives a sense of continuity, a quiet awareness that the present rests on foundations far older than we usually consider. The idea of Valbara also changed how scientists think about the early Earth. For a long time, some researchers believed that plate tectonics might not have been active in the Archaean, or that continents were too small and unstable to assemble into large land masses. Evidence for Valbara suggested that processes resembling modern plate tectonics may have been operating earlier than previously thought, though perhaps in somewhat different forms. This realization opened new questions. How did the formation of early continents affect the chemistry of the oceans and atmosphere? Did larger land masses provide new environments for early life? How did heat flow and mantle convection influence the assembly and breakup of these ancient regions? Each answer leads to more questions, and the story continues to unfold as new data emerges. There is also a certain quiet wonder in knowing that continents can vanish so completely that only scattered fragments remain. We tend to think of continents as permanent features, but in geological time they are temporary arrangements of crust, assembled and dispersed by forces deep within the planet. Vaalbara was one of the earliest of these arrangements, a landmass that existed for hundreds of millions of years and then gradually broke apart, its pieces drifting away to become parts of different continents. Today, those pieces are separated by thousands of kilometers of ocean, yet the rocks remember. In their mineral structures, their chemical compositions and their magnetic signatures, they preserve a record of a time when they were joined. It is a quiet kind of memory, written not in words but in stone, and as scientists continue to study these ancient rocks, new clues still emerge, helping refine our understanding of what that first supercontinent may have looked like, how large it was, and how it changed over time. Trying to imagine the shape of Vaalbara presents a challenge unlike almost any other in geology, because there are no preserved coastlines, no continuous mountain belts stretching across continents, and no broad sedimentary layers that can be traced from one region to another with confidence. Later supercontinents left behind abundant clues, but the farther back in time we look, the more the record becomes fragmented, altered, or erased altogether. In the case of Valbara, scientists are working with only a few surviving pieces of crust, scattered across the globe, each carrying faint hints of a connection that existed more than 3 billion years ago. Reconstructing that world is a bit like trying to assemble a puzzle when most of the pieces are missing, and the ones that remain have been bent, scratched, and partially melted. Yet even with such limitations, patterns begin to emerge, and those patterns allow researchers to sketch a rough picture of what the first supercontinent might have been like. One of the first things to understand is that Valbara was almost certainly smaller than later supercontinents such as Pangaea. The continental crust itself was still developing in the Archaean, and large, stable land masses were relatively rare. Instead of a single enormous expanse of land, Valbara may have resembled a cluster of connected regions, perhaps comparable in size to a modern large continent, but lacking the vast interior plains and complex ecosystems we associate with continents today. The land itself would have looked stark and unfamiliar. Without plants to anchor soil or soften the surface, erosion operated differently. Rain falling on bare rock would have carved channels quickly, carrying sediments directly into the sea. Rivers existed, but they would not have meandered through forests or grasslands. Instead, They likely flowed across rocky terrain, their courses shifting frequently as volcanic activity reshaped the land. Mountain ranges, if present, were probably lower and more rapidly eroded than many of those we see today. The crust was hotter and thinner in places, and tectonic processes may have produced broad volcanic plateaus rather than the towering peaks formed by later continental collisions. Lava flows could cover vast areas, creating landscapes of dark basalt stretching to the horizon. Coastlines, too, would have been very different. Sandy beaches were rare, because sand as we know it often comes from the long breakdown of rocks influenced by biological activity. Instead, shorelines were likely dominated by rocky cliffs, volcanic deposits, and shallow tidal flats rich in minerals. In some of those shallow waters, microbial mats may have formed, quietly building layered structures known as stromatolites, among the earliest visible signs of life on Earth. The oceans surrounding Vaalbara were immense, covering most of the planet's surface. Their chemistry differed from modern seawater, with higher concentrations of dissolved iron and other elements. In certain lighting conditions, the water may have appeared darker or more greenish than the blue we associate with oceans today. Waves rolled across those seas as they do now, driven by wind and tides, but the absence of large marine animals meant the waters were quieter in a way that is difficult to imagine. Understanding the arrangement of land and sea during this time depends heavily on the study of Cratons, those ancient fragments of continental crust that have survived to the present day. The Capval and Pilbara Cratons provide some of the most important clues, but even they do not offer a complete picture. Each preserves only a portion of the original landscape, and both have been altered by billions of years of geological activity. To piece together how these regions might once have fit, scientists examine not only the types of rocks present, but also their ages, structures, and magnetic signatures. When volcanic rocks cool, they lock in a record of Earth's magnetic field at that moment, including the direction of magnetic north and the angle at which the field lines entered the surface. By comparing these magnetic records, researchers can estimate how different pieces of crust were oriented relative to each other in the distant past. This process requires patience and careful interpretation, because rocks can be heated and remagnetized during later geological events, potentially obscuring their original signatures. Still, when multiple lines of evidence point in the same direction, a reconstruction begins to take shape. What emerges is not a precise map with clearly defined borders, but a general sense of proximity and orientation. The Capval and Pilbara Cratons appear to share geological histories that align in both time and structure, suggesting they were once adjacent. Other ancient Cratons may also have been part of the same landmass, though the evidence becomes less certain the farther we look. It is interesting to consider how different the surface of Valbara would have felt compared to modern continents. The air was likely thicker with volcanic gases, and oxygen levels were extremely low. Without an ozone layer to block ultraviolet radiation, sunlight at the surface was harsher, especially during midday. Any life that ventured into shallow waters or onto exposed rocks had to cope with conditions that would seem extreme by today's standards. Weather patterns were influenced by the arrangement of land and sea, but the absence of large forests or grasslands meant less moisture was retained on land. Rainfall may have been intense in some regions, driven by evaporation from warm oceans, but the landscape lacked the vegetation that now moderates runoff and stabilizes soil. Floods could reshape terrain quickly, carving channels that disappeared just as rapidly when volcanic activity altered the topography. Another factor shaping the appearance of Vaalbara was the higher internal heat of the Earth. Mantle plumes, columns of hot material rising from deep within the planet, may have been more common or more vigorous than they are today. When such plumes reached the surface, they could produce massive volcanic eruptions, covering large areas with lava and releasing gases into the atmosphere. These eruptions were not necessarily explosive in the way we often imagine volcanoes. Many would have been effusive, producing broad flows of molten rock that spread slowly across the landscape. cooling into dark, solid layers. Over time, repeated flows could build thick sequences of volcanic rock, forming plateaus that dominated the terrain. Because erosion operated differently without plant life, these volcanic landscapes may have remained relatively sharp and angular, their surfaces broken by fractures and ridges rather than softened by soil and vegetation. Walking across such terrain, if it had been possible, would have felt more like traversing a vast field of hardened lava than hiking through rolling hills. Despite these harsh conditions, the shallow coastal environments of Vaalbara may have been among the most dynamic and biologically active places on the planet. Microbial communities thrived in warm, mineral-rich waters, forming layered structures that slowly grew over years and centuries. These stromatolites, some of which still exist today in a few isolated environments, provide one of the clearest windows into early life. From a distance, such formations might have appeared as low, rounded mounds rising from tidal flats, their surfaces coated with thin films of microorganisms. The scene would have been quiet, almost still, yet full of microscopic activity, life carrying out chemical processes that would eventually transform the atmosphere itself. Imagining the sky above Vaalbara is another exercise in letting go of familiar expectations. Without abundant oxygen, the atmosphere scattered light differently, and the sun itself was slightly dimmer than it is today. The colour of the sky may have been more muted, perhaps tinged with hues shaped by methane and volcanic aerosols. Sunrises and sunsets would still have been beautiful, but in ways subtly different from what we know. The moon, closer to Earth at that time, appeared larger in the sky and exerted stronger tidal forces. Coastal regions experienced more pronounced tides, the shoreline advancing and retreating over greater distances. These tides played an important role in mixing nutrients and creating environments where early life could flourish. As scientists continue to study the surviving fragments of Archaean crust, new details about the possible arrangement of Vaalbara gradually come into focus. Advances in geochronology, isotope analysis and paleomagnetism allow increasingly precise comparisons between distant regions. Each new piece of data adds a small brushstroke to the picture, refining our understanding of a world that left behind so few traces. There is something quietly remarkable about this process. We are reconstructing landscapes that no human eye ever saw, using clues preserved in minerals and rock structures that endured for billions of years. It is a reminder that the Earth itself is a kind of archive, recording its history in layers and crystals, waiting for those who know how to read it. Even so, the image of Vaalbara will probably never be complete. Too much has been lost, too many rocks altered or destroyed. What we have is a sketch rather than a detailed map, an outline of possibilities shaped by careful observation and informed interpretation. Yet that sketch is enough to tell us that the first supercontinent was real, that large land masses were already forming in the Archaean, and that the processes shaping our planet today were already at work, though often in more intense or unfamiliar forms. Beneath parts of the modern continents, hidden under younger layers of rock and soil, there are regions so ancient that they preserve a record of the Earth from a time when the planet itself was still young. These regions are called Cratons, and they are among the most enduring features on the surface of our world. If continents are like books, constantly rewritten by erosion, volcanism and tectonic movement, then Cratons are the oldest surviving pages, worn and faded but still readable if you know how to look closely. To understand why Cratons matter so much in the story of Valbara, it helps to picture how fragile most of Earth's crust actually is. Oceanic crust, for example, is constantly being created at mid-ocean ridges and destroyed at subduction zones. Very little of it survives longer than about 200 million years, which in geological terms is a brief span, barely a paragraph in the history of the planet. Continental crust lasts longer, but even it is often reshaped, buried, or melted over time. Cratons are different. They are thick, stable, and remarkably resistant to the processes that recycle most of the Earth's surface. Some contain rocks more than 3 billion years old, formed during the Archaean eon, when Vaalbara existed. These ancient regions have survived collisions, rifting, erosion, and countless other changes, remaining intact while much of the surrounding crust was altered or destroyed. One reason for this durability lies in their structure. A craton is not just a patch of old rock at the surface. It extends deep into the earth, forming a thick, buoyant root of cool, rigid material that resists deformation. This root, sometimes reaching depths of 200 kilometers or more, makes the craton less likely to be subducted or broken apart. It is, in a sense, anchored more securely than younger, thinner crust. Thinking about this can change the way you imagine the ground beneath your feet. In some parts of the world, the rocks below the soil are not merely old, they're ancient beyond ordinary comprehension, fragments of crust that formed when the atmosphere was still largely devoid of oxygen, and life consisted only of microscopic organisms in the oceans. The Kapval Craton in southern Africa is one of the most famous examples. It contains some of the oldest known rocks on Earth, including sequences that date back more than 3.5 billion years. These rocks preserve evidence of volcanic activity, shallow seas, and even early microbial life. They are like a quiet record of conditions that existed long before plants or animals appeared on land. Far away, in Western Australia, the Pilbara Craton tells a similar story. Its ancient rock formations share striking similarities with those of Kapval, which is one of the reasons scientists suspect that these regions were once connected as part of Valbara. The rocks not only have comparable ages, but also similar compositions and structures, suggesting that they formed in related environments. Standing in either of these places today, you would not immediately recognize their significance. The landscapes are shaped by much more recent processes, and the ancient rocks are often exposed only in certain outcrops or cliffs. Yet beneath the surface lies a foundation that has endured for billions of years, a silent witness to the earliest chapters of Earth's history. It is interesting to consider how these cratons formed in the first place. During the Archaean, the Earth's interior was hotter, and volcanic activity was more widespread. Magma rising from the mantle cooled and crystallized to form new crust, some of which was remelted and reworked multiple times. Through these processes, lighter, more buoyant rocks rich in silica gradually accumulated, forming the earliest continental material. Over time, repeated cycles of melting, intrusion and metamorphism created thick, stable blocks of crust. These blocks were less dense than the surrounding material, and therefore less likely to sink back into the mantle. They became the seeds of continents, the first long-lived fragments of land on a planet that was otherwise in constant motion. The surfaces of these early cratons were very different from the landscapes we know today. Without plants to bind soil or slow erosion, exposed rock weathered in distinctive ways. Rivers carried sediments into shallow seas, where layers of sand, mud, and chemical deposits accumulated. In some places, microbial communities formed stromatolites, leaving behind layered structures that still exist in the fossil record. These environments were among the earliest stable habitats on Earth, and they may have played an important role in the development of life. Shallow coastal waters provided sunlight, nutrients, and relatively calm conditions, allowing microbial ecosystems to thrive. Over millions of years, these organisms gradually altered the chemistry of the oceans and atmosphere, setting the stage for later evolutionary changes. Cratons also preserve evidence of the tectonic processes that shaped the early Earth. Ancient volcanic belts, folded and metamorphosed, record episodes of crustal movement and collision. Granite intrusions mark periods when molten rock rose and cooled within the crust, contributing to its growth and stabilization. Each of these features provides clues about the conditions under which the craton formed. Geologists study these clues using a wide range of techniques. Radiometric dating reveals the ages of minerals, sometimes with precision measured in millions of years, even across spans of billions. Isotope analysis helps determine the sources of magmas, and the temperatures at which rocks formed. Paleomagnetic studies provide information about the positions of continents and the behaviour of Earth's magnetic field in the distant past. All of this work requires patience and careful interpretation. Rocks that are billions of years old have often been altered by later events, heated, compressed, or chemically changed in ways that obscure their original features. Untangling this history is like listening to a faint recording layered with noise, trying to separate the original melody from the distortions added over time. And yet, despite these challenges, the picture that emerges is remarkably coherent. The oldest Cratons formed during a period when the Earth was still cooling and stabilising, when continental crust was beginning to accumulate, and when the processes of plate tectonics were likely already operating in some form. It is worth pausing for a moment to reflect on just how long these rocks have endured. 3 billion years is such an immense span that it is difficult to put into perspective. When those rocks formed, the Sun itself was younger and dimmer. The Moon orbited closer to the Earth, raising stronger tides. The atmosphere contained little oxygen, and the only life on the planet existed in microscopic form. Everything familiar to us, forests, animals, cities, even the shapes of the modern continents, lay far in the future. Yet the Cratons remained. They survived the breakup of ancient continents, the opening and closing of oceans, the rise and erosion of mountain ranges, and the countless climatic changes that reshape the planet's surface. They are, in a sense, the anchors of Earth's geological history, providing continuity across spans of time that would otherwise be almost impossible to reconstruct. Another fascinating aspect of Cratons is the way they influence the landscapes above them even today. Because they are so stable, they often form the cores of modern continents, surrounded by younger rocks that were added later through collisions and volcanic activity. Many of the world's oldest mountain belts and mineral deposits are found in or near Cratonic regions, reflecting the long and complex histories recorded there. Diamonds, for example, are often associated with Cratons. These gemstones form deep within the mantle, under high pressure and temperature, and they are brought to the surface by rare volcanic eruptions known as kimberlite eruptions. The thick, stable roots of Cratons provide the conditions necessary for diamonds to form and survive, which is why major diamond deposits are frequently located in these ancient regions. This connection between deep earth processes and surface features is a reminder that the history of Cratons extends far below the ground we see. Their roots interact with the mantle, influencing heat flow, tectonic behaviour, and even the formation of mineral resources. Returning to the time of Vaalbara, it is likely that the Cratons that formed its core were among the largest and most stable pieces of crust on the planet. Their thickness and buoyancy allowed them to persist, while smaller fragments were recycled or destroyed. As these ancient blocks drifted and collided, they gradually assembled into the first supercontinent, creating a landmass that would endure for hundreds of millions of years before breaking apart again. The idea that continents are built from such ancient components can change the way we think about geography. The continents on a modern map may appear fixed and permanent, but they are really mosaics, assembled from fragments of different ages and origins. Some pieces are relatively young, formed in the last few 100 million years. Others are so old that they date back to the earliest chapters of the planet's history. Cratons are the oldest of these pieces, the deep foundations upon which the rest is built. Imagining their formation and survival also highlights how dynamic the early Earth must have been. Heat rising from the interior drove vigorous mantle convection, volcanic eruptions reshaped the surface, and meteorite impacts were still more common than they are today. In such a world, the stabilization of large blocks of crust was a significant development, marking a transition toward the more organized tectonic behavior that would later produce vast continents and mountain ranges. And yet, even these ancient foundations were not entirely immune to change. Over billions of years, Cratons have been fractured, uplifted, and eroded. Sediments have been deposited on their surfaces and later stripped away. Younger rocks have been added along their margins, expanding the continents outward. The story of a Craton is not one of complete stillness, but of resilience, of enduring through change rather than avoiding it altogether. There is something quietly comforting in that idea. Stability does not mean remaining untouched. It means persisting through transformation, carrying the memory of the past forward into the present. As scientists continue to study Cratons around the world, new discoveries are still being made. Improved analytical techniques allow researchers to examine minerals at ever finer scales, revealing details about the conditions under which they formed. Each new piece of data adds depth to our understanding of the early Earth and the processes that shaped it. These ancient rocks are not merely relics, they are active sources of knowledge, helping us understand how continents form, how plate tectonics operates, and how the environments that support life came into being. Long before forests, animals, or even stable shorelines became familiar features of Earth, the planet's surface was shaped primarily by heat rising from within. The young Earth was not a quiet world. It was restless, active, and often violent in ways that are difficult to imagine from the relatively stable landscapes most of us know today. Volcanoes were not isolated features scattered here and there. In many regions, they were part of the background rhythm of the planet, erupting, cooling, and erupting again as the interior slowly released the immense heat left over from Earth's formation. To understand why this early world was so geologically active, it helps to begin deep below the surface, in the mantle. The mantle is not liquid in the way magma is liquid, but over long periods it behaves like a very thick, slowly flowing substance. Heat from the planet's core and from radioactive elements causes parts of the mantle to become buoyant and rise, while cooler material sinks. This slow circulation, called convection, is the engine that drives plate tectonics and volcanic activity. In the Archaean eon, when Valbara existed, the mantle was significantly hotter than it is today. Earth had formed only a little over 1 billion years earlier, and much of the heat generated by planetary accretion and core formation was still being released. Radioactive decay was also more intense, because many short-lived isotopes that have since disappeared were still present in large quantities. A hotter mantle meant that convection currents were stronger and more vigorous. Magma formed more easily and in greater volumes, and volcanic eruptions were likely more frequent. In some regions, enormous outpourings of lava may have covered vast areas, creating thick sequences of volcanic rock that still form part of ancient Cratons today. One of the most remarkable pieces of evidence for this hotter world comes from a type of volcanic rock called Meteorite. These rocks are rare today because they require extremely high temperatures to form, temperatures hotter than most modern mantle melts. Yet Meteorites are relatively common in Archaean rock formations, suggesting that the mantle was capable of producing lavas far hotter and more fluid than those we usually see now. When Meteorite lava erupted, it flowed very quickly, sometimes moving almost like water across the surface, before cooling and solidifying. These flows could spread over large distances, creating broad volcanic plains. Imagining such eruptions can give a sense of how different the landscapes of early Earth must have been. Wide expanses of dark, newly solidified rock stretching to the horizon, still warm in places, with steam rising where rain or seawater met the cooling surface. Volcanoes also played a central role in shaping the atmosphere. Each eruption released gases trapped within the magma, including water vapour, carbon dioxide, sulfur compounds, and nitrogen. Over millions of years, this outgassing gradually built the atmosphere and contributed to the formation of the oceans. Without volcanoes, the surface of Earth might have remained dry and airless, more like the moon than the world we know. The gases released by early volcanoes created an atmosphere very different from today's. Oxygen was almost entirely absent, and the sky may have appeared hazy or tinted, influenced by methane and volcanic aerosols. The air would have smelled strongly of sulfur in many places, especially near active volcanic regions. It is interesting to pause and imagine the sound of such a world. Eruptions might have been heard as distant rumbles, punctuated by the cracking of cooling lava or the hiss of steam escaping from fissures. Thunderstorms may have been frequent, driven by heat rising from warm oceans and volcanic landscapes. Lightning would have flashed across skies that no birds crossed. No leaves stirred beneath, only wind moving over bare rock. Another reason the early Earth was so geologically restless lies in the behaviour of the crust itself. Because the planet was hotter, the crust was generally thinner and more prone to breaking and recycling. New crust formed at volcanic centres and was often drawn back into the mantle relatively quickly. Stable continental crust existed, but it was still developing, still gathering into the larger fragments that would eventually assemble into Vaalbara. This constant creation and destruction of crust meant that landscapes changed over timescales that, while still long by human standards, were rapid in geological terms. Volcanic islands rose and sank. Lava flows buried older rock. Faults opened and shifted. The surface was always in motion, always adjusting. Meteorite impacts also contributed to this restless environment. In the early history of the solar system, many leftover fragments from planetary formation still orbited the Sun. Earth was struck more frequently than it is today, and some of those impacts released enormous amounts of energy, melting rock and reshaping large areas of the surface. Although the most intense period of bombardment had largely ended before the time of Valbara, impacts were still more common than in later eras. Each one added to the heat and disruption already present from volcanic activity. There is another aspect of early Earth's heat that is easy to overlook, and that is the heat stored within the thick roots of forming Cratons. These ancient blocks of crust acted in some ways like insulating blankets, slowing the escape of heat from the mantle beneath them. Over time, this could lead to the build-up of thermal energy that eventually contributed to rifting and volcanic activity along the edges of these early continental fragments. In this way, the processes that created stable land masses also helped generate the forces that would later reshape them. Continents were not permanent fixtures even then. They formed, changed, and sometimes broke apart, all driven by the slow circulation of heat deep within the planet. Volcanic activity also influenced the chemistry of the oceans. When lava erupted underwater, it interacted directly with seawater, releasing minerals and altering the composition of the surrounding environment. Hydrothermal vents, where hot water rich in dissolved elements flowed from the seafloor, were likely widespread. These environments may have played an important role in the early evolution of life, providing energy and nutrients in otherwise dark regions of the ocean. Shallow seas near volcanic coastlines were especially dynamic places. Ash and minerals carried by rivers and eruptions accumulated in layers, creating sediments that would later harden into rock. Microbial communities thrived in these nutrient-rich waters, forming mats and stromatolites that slowly grew layer by layer, recording their existence in stone. The combination of volcanic heat, mineral-rich water, and sunlight created environments where life could persist, even in a world that might otherwise seem harsh and inhospitable. It is a quiet reminder that life does not always require gentle conditions. Sometimes it flourishes in places shaped by fire and change. Another difference between early Earth and the present lies in the style of volcanism itself. Today, many volcanic eruptions are associated with well-defined plate boundaries, such as subduction zones or mid-ocean ridges. In the Archaean, plate tectonics may have operated somewhat differently, and mantle plumes, large upwellings of hot material rising from deep within the Earth, may have been more common or more active. These plumes could produce massive volcanic provinces, covering enormous areas with lava over relatively short geological intervals. The landscapes created by such events would have been vast and relatively featureless, broken only by fissures, vents, and occasional elevated regions where magma accumulated. Because there was little vegetation to slow erosion, rainfall could rapidly carve channels into newly formed volcanic rock, carrying sediments into nearby basins. Over time, these sediments built thick layers that preserved a record of the environment in which they formed, giving modern scientists clues about the conditions that existed billions of years ago. It is remarkable that any of these records survive at all. Over such immense spans of time, most rocks are altered, buried, or destroyed. The fragments that remain, preserved in ancient Cratons, are precious windows into a world that would otherwise be almost impossible to imagine. The restlessness of early Earth was not constant in the sense of continuous eruptions everywhere at once. There were periods of relative quiet, times when lava flows cooled and landscapes stabilized for a while. But compared to the modern world, the level of activity was much higher, and the intervals between major events were often shorter. Even the interior of the planet was evolving during this time. As heat gradually escaped into space, the mantle cooled, convection slowed slightly, and the style of tectonic activity began to shift toward the patterns we recognize today. The formation of larger, more stable continents was part of this long transition from a hotter, more chaotic early Earth to a somewhat more stable planet. Yet stability is always relative. The processes that shaped Vaalbara did not stop when that early supercontinent formed. Volcanoes continued to erupt, plates continued to move, and the interior of the Earth continued to release heat. The landscapes of that time were never static. They were always in motion, always changing. It is interesting to think about how different the night sky might have looked to an observer standing on Valbara, if such an observer had existed. With no artificial lights and little oxygen in the atmosphere, the stars would have appeared brilliant and sharp. The moon, closer than it is today, would have dominated the sky, its tides pulling strongly on the oceans below. Occasionally a bright meteor might have streaked across the darkness, a reminder that the solar system was still settling into its present form. Meanwhile, beneath that sky, lava might have glowed faintly in the distance, and the ground itself might have felt warm in places, heat rising slowly from the interior of a planet still cooling from its birth. Considering all of this together, it becomes clear why early Earth was so geologically restless. The combination of higher internal heat, vigorous mantle convection, frequent volcanic activity, and a thinner, more dynamic crust created a world in which change was constant. Landscapes formed and were reshaped again and again, and the conditions that would eventually allow more complex life to evolve were being prepared, step by slow step, by processes driven deep within the planet. Looking upward from the surface of the Archaean Earth, the sky would not have appeared the way it does today. The familiar pale blue, the crisp clarity of a dry morning, even the deep twilight hues we recognize at sunset all depend on the composition of the atmosphere, and 3 billion years ago the composition was profoundly different. Oxygen, the gas that now makes up about 21% of the air, was almost entirely absent. The world of Valbara existed beneath a sky shaped by other gases, other processes, and a balance of chemistry that would feel unfamiliar in nearly every way. To understand how that atmosphere formed, it helps to step back once again to the early stages of the planet's history. When Earth first formed, it likely possessed a thin, temporary atmosphere composed mainly of hydrogen and helium, captured from the surrounding solar nebula. But the young sun was far more active than it is now, releasing strong solar winds that stripped much of this light atmosphere away. Without a strong magnetic field at that time, Earth could not easily hold on to those gases. What replaced it was an atmosphere created gradually from within the planet itself. Volcanoes, so abundant during the Archaean, released vast quantities of gas trapped in molten rock. Each eruption added water vapour, carbon dioxide, nitrogen, sulfur compounds, and traces of methane and ammonia. Over millions of years, these emissions accumulated, forming a dense and complex atmosphere quite unlike the one we breathe today. If you could have stood on the shoreline of Vaalbara and taken a breath, it would not have been breathable in the modern sense. Oxygen levels were so low that complex animals could not have survived. The air may have felt heavier, humid in many places, with a faint haze drifting through the sky. Volcanic gases and fine particles suspended in the atmosphere could have scattered sunlight differently, giving the sky a muted or slightly tinted appearance. The colour of that sky is something scientists still debate. Some models suggest it may have been more orange or reddish under certain conditions, influenced by methane and other hydrocarbons reacting in the upper atmosphere. Others propose a pale, hazy tone, with sunlight filtered through layers of particles. What seems certain is that it would not have been the bright, clear blue we associate with modern Earth, because that blue colour depends strongly on the presence of oxygen and the structure of the atmosphere that developed later. Another important difference was the absence of an ozone layer. Today, high in the atmosphere, ozone absorbs much of the sun's ultraviolet radiation, protecting life at the surface. In the Archaean, without abundant oxygen to form ozone, more ultraviolet light reached the ground and the surface of the oceans. This radiation posed a challenge for early life, which is one reason many of the earliest organisms lived in water, where even a few centimetres of depth provided some protection from harmful rays. Despite these harsh conditions, the atmosphere was not hostile to all forms of life. In fact, it was part of an environment in which microbial organisms were already thriving. Some of these microbes, particularly cyanobacteria, were beginning to use sunlight to split water molecules, releasing oxygen as a byproduct. At first, this oxygen did not accumulate in the atmosphere. Instead, it reacted with dissolved iron in the oceans, forming iron oxides that settled to the seafloor in layers now known as banded iron formations. These deposits are among the most striking geological records of early atmospheric chemistry. When viewed in cross-section, they appear as alternating layers of reddish iron-rich minerals and darker silica, a rhythmic pattern laid down over immense spans of time. Each layer is a quiet testimony to the gradual changes taking place in the oceans and atmosphere, changes driven by microscopic organisms carrying out photosynthesis in shallow seas. It is remarkable to think that the transformation of the atmosphere, one of the most profound changes in Earth's history, was set in motion by life too small to see with the naked eye. The oxygen released by these early microbes would eventually reshape the planet, but during the time of Vaalbara, that process was only just beginning. Carbon dioxide was likely far more abundant in the Archaean atmosphere than it is today, and this played an important role in maintaining the planet's temperature. The sun, being younger, produced less energy than it does now, a situation sometimes referred to as the faint young sun paradox. With a dimmer sun, Earth should have been frozen solid, yet geological evidence shows that liquid water existed. The higher concentration of greenhouse gases, including carbon dioxide and possibly methane, helped trap heat, keeping the oceans from freezing over completely. Methane, produced both by volcanic activity and by certain microorganisms, may have been particularly significant. In an oxygen-poor atmosphere, methane can accumulate to levels much higher than those possible today. Some scientists believe that methane haze could have formed in the upper atmosphere, somewhat like the orange haze seen on Saturn's moon Titan, filtering sunlight and affecting climate in ways we are still working to understand. Clouds, too, would have been part of that ancient sky. Water vapour released by volcanoes and evaporating oceans condensed into clouds much as it does today. Rain fell, sometimes in heavy downpours, eroding volcanic landscapes and carrying minerals into the seas. The hydrological cycle was already in motion, driven by the same basic principles that govern it now, though under different atmospheric conditions. Thunderstorms may have been frequent in some regions, especially over warm oceans where evaporation was intense. Lightning flashing across a hazy sky would have illuminated landscapes of bare rock and steaming volcanic fields, brief bursts of brightness in a world otherwise dominated by subtle, earthy tones. The composition of the air also influenced sound and smell in ways that are difficult to imagine. Higher concentrations of certain gases could have carried the scent of sulfur or other volcanic compounds across the land. Sound may have travelled slightly differently in denser, more humid air, though the absence of animals meant the soundscape itself was sparse, shaped mostly by wind, water, and geological activity. Nightfall on the Archaean Earth would have brought its own distinctive atmosphere, both literally and figuratively. With little oxygen and fewer airborne particles of the kinds produced by plants and modern ecosystems, the night sky may have appeared exceptionally clear in some regions. Stars would have shone sharply, and the moon, closer than it is now, would have appeared larger, its light reflecting off oceans that stretched across most of the planet. The tides raised by that nearer moon were stronger, and the interaction between tides and atmosphere influenced coastal environments in subtle ways. Tidal flats exposed and submerged twice each day provided habitats for microbial communities, while the mixing of seawater helped distribute nutrients. The atmosphere, oceans, and crust were all part of a connected system, each influencing the others over long spans of time. One of the most interesting aspects of the Archaean atmosphere is how gradually it changed. There was no single moment when oxygen suddenly appeared, or when methane suddenly vanished. Instead, the transformation unfolded over hundreds of millions of years, shaped by the balance between volcanic outgassing, chemical reactions in the oceans, and the slow work of photosynthetic microbes. Eventually, oxygen would begin to accumulate in the atmosphere in what is known as the Great Oxidation Event, but that lay far in the future relative to the time of Vaalbara. During the period we're imagining now, the atmosphere remained largely anoxic, a word scientists use to describe environments lacking oxygen. This lack of oxygen also meant that many chemical processes operated differently. Minerals that would quickly oxidize in modern air could persist unchanged. Iron, for example, remained dissolved in seawater until oxygen produced by microbes caused it to precipitate. These differences in chemistry are recorded in ancient rocks, providing clues about the composition of the atmosphere and oceans at the time. Another subtle but important factor was the interaction between the atmosphere and the planet's magnetic field. By the Archaean, Earth had developed a magnetic field generated by the motion of molten iron in its outer core. This magnetic field deflected much of the solar wind, helping to prevent the atmosphere from being stripped away, as had likely happened to Mars to a significant degree. Without that protection, the atmosphere of early Earth might have been far thinner, and the conditions necessary for oceans and life might not have persisted. Thinking about this interplay between the deep interior, the surface, and the sky can give a sense of how interconnected the planet has always been. Heat rising from the mantle drives volcanism. Volcanoes release gases that shape the atmosphere. The atmosphere influences climate and the chemistry of the oceans. The oceans support life, and life in turn alters the atmosphere. It is a continuous cycle, unfolding over immense spans of time. Imagining a day on Valbara beneath that oxygen-poor sky invites a quiet kind of reflection. Morning light would spread across rocky terrain, filtered through a hazy atmosphere. The air might feel warm and heavy, carrying the faint scent of volcanic gases. Waves would move steadily along dark coastlines, and in shallow waters, microbial mats would carry out the slow work of photosynthesis, releasing tiny amounts of oxygen that quickly reacted with minerals in the sea. As the sun climbed higher, ultraviolet radiation would intensify, making exposed surfaces harsh environments for most forms of life. Yet in sheltered pools and beneath the water's surface, microscopic communities would continue to thrive, largely unaffected by conditions that would seem extreme to us. Evening would bring a gradual cooling, the sky shifting in colour as sunlight passed through layers of gas and particles. Stars would appear, bright and numerous, and the moon would rise, larger than we are accustomed to seeing, its gravity tugging at the oceans and shaping the rhythm of tides along the coasts. All of this was part of the world in which the first supercontinent existed, a world where the atmosphere was still evolving, still being shaped by geological and biological processes that would eventually transform the planet. Long before fish moved through coral reefs or whales crossed open seas, the oceans of Earth were already vast, already restless, already shaping the surface of the planet in ways that would echo through billions of years. During the time of Vaalbara, these oceans were not the clear blue waters we're used to imagining. Their chemistry was different, their colours may have been different, and the life within them was microscopic, subtle, and easy to overlook, yet quietly transforming the world. To picture these early oceans, it helps to begin with their origin. Water did not simply appear on the surface of Earth all at once. Much of it came from volcanic outgassing, released as water vapour from magma deep within the planet. As the surface cooled, that vapour condensed, forming clouds and falling as rain, sometimes for immense stretches of time. Some water may also have been delivered by icy comets and water-rich asteroids in the early history of the solar system, adding to what volcanoes released. Over millions of years, rain filled the lowest regions of the crust, forming the first oceans. These basins were not as stable or well-defined as modern ocean basins. The crust was thinner and more dynamic, and the boundaries between land and sea shifted as volcanic activity and tectonic movement reshaped the surface. Once oceans existed, they quickly became central to the planet's chemistry. Water is an excellent solvent, capable of dissolving minerals from rocks and carrying them into solution. Rivers, rainwater, and hydrothermal vents all contributed elements to the seas, creating a chemical mixture quite unlike the seawater we know today. One of the most important differences was the abundance of dissolved iron. In the absence of oxygen, iron remained soluble in seawater, giving some regions of the ocean a darker or greenish tint. When oxygen produced by early photosynthetic microbes began to accumulate locally, it reacted with this dissolved iron, forming iron oxides that settled to the sea floor. Over time, these processes created the banded iron formations that still exist in ancient rocks, alternating layers of iron-rich minerals and silica that record cycles of chemical change in the early oceans. If you could have looked across a shallow Archaean sea, the water might not have appeared blue at all. Depending on the concentration of minerals and the angle of sunlight filtering through a hazy atmosphere, it could have looked darker, perhaps tinged with green or brown in certain areas. Suspended particles from volcanic ash and chemical reactions may have given the water a cloudy appearance, especially near active regions. The temperature of these early oceans is another subject of careful scientific study. Some evidence suggests they may have been warmer than modern oceans, perhaps significantly so due to higher levels of greenhouse gases in the atmosphere and greater heat flow from the Earth's interior. Warm water can hold less dissolved oxygen, which may have reinforced the low oxygen conditions that characterized much of the Archaean. Hydrothermal vents played a particularly important role in shaping ocean chemistry. Along mid-ocean ridges and volcanic regions, seawater circulated through cracks in the crust, heated by underlying magma, and emerged again rich in dissolved metals and minerals. These vents created environments where chemical energy was abundant, providing potential habitats for early life. Even today, hydrothermal vent communities thrive in complete darkness, relying not on sunlight but on chemical reactions for energy. It is possible that similar environments in the Archaean supported some of the earliest living systems, though exactly how life began remains one of the most intriguing and challenging questions in science. In shallow coastal waters, conditions were different. Sunlight penetrated the upper layers of the ocean, and microbial mats flourished on tidal flats and submerged surfaces. These mats were composed of countless microorganisms living together, trapping sediments and forming layered structures that could grow over time into stromatolites. Stromatolites are among the most recognizable fossils from the Archaean world. At first glance, they resemble rounded mounds or layered domes of stone, but each layer represents the activity of living organisms, trapping particles and precipitating minerals as they grew. Some modern stromatolites still exist in a few isolated environments, offering a glimpse of processes that were once widespread. The interaction between oceans and atmosphere was constant and dynamic. gases dissolved in seawater, and chemical reactions in the oceans influenced the composition of the air above. Carbon dioxide, for example, dissolved in seawater and participated in chemical cycles that helped regulate the planet's temperature over long timescales. Waves moved across these ancient seas much as they do today, driven by wind and shaped by the contours of the coastline. Tides, influenced by a closer moon, were stronger, especially in shallow regions. The rise and fall of the water exposed tidal flats twice each day, creating environments where minerals, water, and microorganisms interacted in cycles that may have been crucial for early biochemical processes. It is interesting to imagine the sounds of such a shoreline. Without the calls of seabirds or the movement of animals, the dominant sounds would have been wind, waves, and perhaps the distant rumble of volcanic activity. The air might have carried the scent of salt mixed with sulfur from nearby vents or eruptions. Rain falling on bare rock would have washed minerals into the sea, gradually building sediments that settled in layers on the ocean floor. Over immense spans of time, these sediments hardened into rock, preserving records of ocean chemistry and climate that scientists can still study today. One of the challenges in reconstructing the early oceans is that much of the seafloor from that time has been recycled back into the mantle through subduction. Unlike continental crust, oceanic crust is relatively short-lived, and rocks older than about 200 million years are rare on the modern seafloor. As a result, much of what we know about Archaean oceans comes from sediments and volcanic rocks preserved on ancient Cratons, which were once part of coastal or shallow marine environments. These records reveal a world where the chemistry of the oceans was in constant flux. Oxygen levels were extremely low, and the balance between different elements shifted as volcanic activity, weathering, and microbial processes interacted. Sulfur compounds, methane, and iron played larger roles than they do today, and the biological communities that existed were adapted to these conditions. Another difference between early oceans and modern ones lies in the absence of large predators or complex food webs. The ecosystems of the Archaean were dominated by microorganisms, forming communities that relied on chemical and solar energy. These communities may have looked simple, but their impact on the planet was profound, gradually altering the atmosphere and paving the way for more complex life. The clarity of the water likely varied greatly from place to place. Near volcanic regions or river mouths, suspended particles could make the water murky. In deeper, quieter areas, the water may have been clearer, though still tinted by dissolved minerals. Sunlight penetrating the upper layers would have created zones where photosynthetic microbes thrived, while deeper regions remained dark and dominated by chemical processes. Currents in these early oceans were influenced by the arrangement of land and sea, the rotation of the planet, and differences in temperature and salinity. Although the details are difficult to reconstruct, it is likely that ocean circulation played an important role in distributing heat around the planet, helping to moderate climate despite the faint young sun. Thinking about these oceans can give a sense of how interconnected Earth systems have always been. Volcanoes released gases and minerals, rain and rivers carried materials into the sea, microorganisms used sunlight and chemical energy to grow, altering the chemistry of their surroundings. Sediments accumulated, recording the passage of time in layers that would later become rock. All of these processes were already underway during the time of Vaalbara, shaping a world that was still in its early stages, still evolving, still preparing the conditions that would eventually allow more complex life to appear. If you imagine standing on a rocky shoreline of that ancient continent, watching waves move across dark water under a hazy sky, it might feel quiet, almost empty, yet full of unseen activity. Beneath the surface, countless microorganisms were carrying out the slow work of transformation, molecule by molecule, generation after generation. If you could peer into the shallow waters of Earth more than 3 billion years ago, you would not see fish, plants, or anything large enough to notice at first glance. At first, the scene might appear almost empty, just ripples of water moving across mineral-stained rock, sunlight filtering down through a hazy atmosphere, and perhaps thin films clinging to submerged surfaces. Yet within those films, and drifting invisibly in the water itself, life was already present. It was small, simple, and silent, but it had begun one of the most important processes in the history of the planet. Understanding how life existed in such a harsh and unfamiliar world requires letting go of many of the assumptions we naturally carry. When we think about living things, we often imagine animals moving, plants growing, or at least something visible to the eye. But for most of Earth's history, life was microbial. Tiny organisms, often consisting of a single cell, dominated the biosphere for billions of years. They lived in environments that would seem extreme by modern standards, yet to them those conditions were simply normal. The Archaean Earth, during the time of Vaalbara, offered few comforts. Oxygen was scarce in the atmosphere and oceans. Ultraviolet radiation from the sun was stronger at the surface. Volcanic activity was common, releasing gases and altering the chemistry of both air and water. Temperatures in some regions may have been higher than today, and the oceans were rich in dissolved minerals, including iron and sulfur compounds. And yet, life found ways to persist. The earliest organisms were likely prokaryotes, cells without a nucleus, similar in many ways to modern bacteria and archaea. These organisms were extraordinarily adaptable. Some obtained energy by breaking down chemical compounds dissolved in water, a process known as chemosynthesis. Others used sunlight, capturing energy through primitive forms of photosynthesis that did not yet produce oxygen. These microbial communities were not isolated individuals drifting alone. Many formed mats, dense layers of cells bound together by sticky substances they secreted. These mats could grow across rocks and shallow water, trapping sediments and creating stable environments in which microorganisms could thrive. In such communities, different species often lived side by side, each carrying out chemical reactions that benefited the others. It is interesting to think of these mats as some of the earliest ecosystems, though they would not have looked like ecosystems in the modern sense. There were no plants casting shade, no animals grazing or hunting. Instead, there were layers of microorganisms, each adapted to slightly different conditions of light, temperature, and chemistry. The upper layers might contain cells capable of using sunlight, while deeper layers relied on chemical reactions in low oxygen conditions. In a way, these mats were like living cities, but on a microscopic scale, with nutrients and gases flowing between layers and countless cells dividing and growing in slow, steady rhythms. One of the challenges faced by early life was the intensity of ultraviolet radiation. Without an ozone layer, more of this radiation reached the surface of the oceans. Water provided some protection, and many microorganisms lived just below the surface, where sunlight was still available, but harmful radiation was reduced. Others may have produced pigments or protective compounds that helped shield them from damage. Heat was another factor. Hydrothermal vents on the seafloor released superheated, mineral-rich water, creating environments where temperatures could be extreme. Yet modern studies of extremophiles, organisms that thrive in harsh conditions, show that life can adapt to temperatures well above what was once thought possible. It is entirely plausible that similar organisms existed in the Archaean, living in and around these vents, drawing energy from chemical reactions rather than sunlight. These vent environments are especially intriguing because they may resemble the conditions in which life first originated. The mixing of hot, mineral-rich water with cooler seawater creates steep chemical gradients, providing energy that microorganisms can exploit. Some scientists believe that the earliest life forms may have emerged in such settings, though the exact location and mechanism of life's origin remain subjects of active research. Another source of energy came from sunlight, and this is where one of the most significant developments in Earth's history began. Certain microorganisms evolved the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into organic molecules. Early forms of photosynthesis did not release oxygen, but later cyanobacteria developed a version that did. At first, the oxygen produced by these microbes did not accumulate in the atmosphere. Instead, it reacted with dissolved iron in the oceans, forming iron oxides that settled to the sea floor. This process continued for millions of years, gradually removing iron from seawater and laying down the banded iron formations that geologists study today. It is remarkable to consider that these microscopic organisms, drifting in shallow seas or clinging to rocks, were slowly altering the chemistry of an entire planet. They did not do this intentionally, of course. They were simply carrying out metabolic processes that allowed them to survive and reproduce. Yet the byproducts of those processes would eventually transform the atmosphere, paving the way for more complex life. Life in the Archaean was not limited to warm, shallow waters. Microorganisms likely inhabited a wide range of environments, from hot springs to deep-sea vents to sediments beneath the ocean floor. Some may have lived within rocks themselves, in tiny pores filled with water and nutrients. These hidden habitats provided protection from radiation and temperature fluctuations, creating stable microenvironments where life could persist. One of the fascinating aspects of microbial life is how quickly populations can grow under favourable conditions. A single cell dividing repeatedly can produce millions of descendants in a relatively short time, at least by geological standards. Over thousands or millions of years, such growth could cover large areas of the seafloor or coastal regions with microbial communities. Despite their abundance, these organisms left relatively few visible traces. Fossils of individual cells are rare and often difficult to interpret. Most of what we know about early life comes from indirect evidence, chemical signatures preserved in rocks, layered structures formed by microbial mats, and isotopic ratios that suggest biological activity. Isotopes are atoms of the same element with different numbers of neutrons, and living organisms often prefer certain isotopes over others in their metabolic processes. By studying the ratios of isotopes in ancient rocks, scientists can infer whether biological activity was present when those rocks formed. These subtle clues, measured with precise instruments, provide some of the strongest evidence for life in the Archaean. Imagining the daily rhythm of this microscopic world requires a shift in perspective. There were no days in the sense of schedules or routines, but there were cycles of light and darkness, tides rising and falling, temperatures changing with the movement of the sun. Microorganisms responded to these cycles, adjusting their metabolic processes, growing when conditions were favourable, and entering dormant states when they were not. In shallow coastal regions, tides may have played an important role. As water levels rose and fell, microbial mats were alternately submerged and exposed, experiencing changes in temperature, salinity, and light. These fluctuations created challenges, but also opportunities, encouraging the evolution of adaptations that allowed organisms to survive in variable environments. Storms too influenced the distribution of life. Heavy rains and strong winds could stir up sediments, carrying nutrients into the oceans and reshaping coastal habitats. Volcanic eruptions added minerals and heat, sometimes disrupting local ecosystems but also creating new environments where life could take hold. There is something quietly reassuring about the resilience of these early organisms. They survived in a world without oxygen, without complex food webs, without the stability we often associate with habitable environments. They adapted to heat, radiation, and chemical extremes, demonstrating that life, once established, can be remarkably persistent. It is also worth remembering that evolution was already at work. Even in this early period, mutations occurred. Natural selection favoured certain traits, and populations gradually changed over generations. The pace of these changes was slow, measured in thousands or millions of years, but over long spans of time, the cumulative effect was profound. The diversity of microbial life in the Archaean was likely greater than we once imagined. Modern studies of extreme environments, from deep-sea vents to acidic hot springs, reveal astonishing varieties of microorganisms, many of which were unknown until recently. It is reasonable to think that the Archaean oceans hosted similarly diverse communities, adapted to a wide range of conditions. Another intriguing aspect of early life is the role of cooperation. Microbial communities often rely on metabolic interactions, where the waste products of one organism serve as nutrients for another. These relationships can create stable systems in which multiple species coexist, each contributing to the overall functioning of the community. In a sense, the earliest ecosystems were built on cooperation long before competition became the dominant theme in more complex food webs. Life was less about predators and prey, and more about networks of chemical exchange, energy flowing through communities in ways that were subtle but effective. If you imagine standing on a rocky shoreline of Valbara and looking out over the water, it might seem like a quiet, empty world. The waves would move steadily, the sky above hazy and unfamiliar, the land barren and dark. Yet beneath the surface, countless microorganisms were living, dividing, and evolving, shaping the chemistry of the oceans and atmosphere in ways that would eventually change the entire planet. Time, in that world, moved slowly by human standards but quickly by microbial ones. Generations passed in hours or days, and over millions of years these tiny organisms transformed their environment step by step, molecule by molecule. One of the most visible results of their activity was the formation of layered structures in shallow waters, built as microbial mats trapped sediments and precipitated minerals. These structures, which could grow slowly over long periods, became some of the earliest macroscopic evidence of life, preserved in stone and still visible today in certain parts of the world. Layer upon layer, those early microbial communities left behind structures that endured long after the organisms themselves had vanished. These structures are called stromatolites, and they represent one of the clearest and most tangible records of life in the Archaean world. At first glance, a stromatolite might not seem especially remarkable. It can look like a low, rounded mound of stone, sometimes shaped like a dome or a gently stacked series of ridges. Yet each layer within it is the result of countless microscopic cells living, growing, and interacting with their environment over long stretches of time. To understand how stromatolites formed, it helps to picture a shallow coastal environment on the edge of Vaalbara. The water is warm and mineral-rich. Sunlight reaches the seafloor in clear patches, while tides slowly rise and fall, exposing surfaces for part of each day. On submerged rocks or sediments, thin microbial mats begin to grow. These mats are made largely of cyanobacteria and other microorganisms that secrete sticky substances, helping them cling to surfaces and to each other. As currents carry fine grains of sediment through the water, these particles become trapped in the sticky surface of the mat. The microbes continue to grow upward, reaching toward the light, and in doing so they cover the trapped sediment with a new layer of living cells. More sediment settles and the process repeats. Over time, this slow cycle builds a laminated structure, each layer preserving a moment in the interaction between life and its environment. It is important to remember that this process is extraordinarily gradual. A stromatolite does not form in a year or even in a decade. Growth may be measured in millimeters over many years, depending on conditions. Yet given thousands or millions of years, these tiny increments accumulate into structures large enough to be preserved in the geological record. One of the remarkable things about stromatolites is that they are not fossils in the usual sense. They are not the preserved remains of individual organisms like shells or bones. Instead, they are records of activity, the result of countless generations of microorganisms carrying out their daily processes, trapping sediments, precipitating minerals, and slowly building a structure that reflects both biological and environmental influences. Examining a cross-section of a stromatolite reveals delicate layers, sometimes only fractions of a millimeter thick. These layers may vary in composition, colour and texture, depending on changes in sediment supply, water chemistry and microbial activity. In this way, stromatolites act almost like diaries of ancient shorelines, recording cycles of tides, storms, and seasonal variations that occurred billions of years ago. The cyanobacteria that played a major role in building many stromatolites were also among the earliest organisms to produce oxygen through photosynthesis. This does not mean that oxygen immediately filled the atmosphere. For a long time, most of the oxygen released reacted with dissolved iron and other elements in the oceans. Still, the steady production of oxygen in countless microbial mats represented a turning point, even if the full consequences would not become visible for hundreds of millions of years. Thinking about the scale of this process can be quietly astonishing. Imagine a thin film of microorganisms growing across a tidal flat, releasing tiny amounts of oxygen each day, trapping grains of sediment, and slowly building a structure that might persist for billions of years. No single organism intended to transform the planet, yet collectively, through ordinary metabolic processes repeated endlessly, they set in motion changes that would reshape the atmosphere, the oceans, and eventually the course of evolution itself. Stromatolites also tell us something about the environments in which early life thrived. Most formed in shallow, sunlit waters, where microbial mats could receive enough light for photosynthesis. These environments were often relatively calm, because strong waves or currents could disrupt the delicate mats before they had time to stabilize sediments. Lagoons, tidal flats, and protected coastal areas were especially favorable settings. At times, storms or shifts in sea level would bury parts of these structures, protecting them from erosion and allowing them to be preserved. Over immense spans of time, layers of sediment accumulated above and around them, eventually hardening into rock. When geologists discover stromatolites today, they are often embedded within ancient sedimentary formations that were once shallow seas along the edges of long-vanished continents. It is worth noting that stromatolites are not merely relics of the distant past. In a few places on Earth, they still form today. One of the most famous examples is found in Shark Bay, Western Australia, where modern stromatolites grow in hypersaline waters that discourage grazing animals. These living stromatolites provide a window into processes that were once widespread in the Archaean oceans. Watching modern stromatolites grow is a lesson in patience. Changes are subtle and slow, often invisible over the course of a single day or even a year. Yet over decades, the structures become more pronounced, their layered forms gradually emerging as sediments are trapped and microbial communities expand. Observing them can give a sense of how similar processes might have unfolded on a much larger scale billions of years ago. Another intriguing aspect of stromatolites is how they reflect the interplay between biology and geology. The microorganisms depended on their environment for nutrients, light, and suitable temperatures. At the same time, their activity altered that environment, changing local chemistry, influencing sediment deposition, and contributing to the gradual oxygenation of the oceans. This feedback between living systems and their surroundings is a theme that runs throughout Earth's history. Life does not simply adapt to the planet, it also helps shape it. Stromatolites are among the earliest and most visible examples of this relationship, showing how even the smallest organisms can leave lasting marks on the geological record. Considering the timescales involved can also change how we think about progress and change. Human activities often produce visible results in years or decades, but stromatolites remind us that some of the most profound transformations occur through processes so slow that they are almost imperceptible from one moment to the next. Layer by layer, generation by generation, the cumulative effect becomes immense. The presence of stromatolites in rocks more than 3 billion years old also provides evidence that life was already well established by that time. The organisms capable of forming these structures were not the first life on Earth. They were part of ecosystems that had already been evolving for millions of years. This pushes the origin of life even further back, into periods for which direct evidence is scarce, but increasingly suggested by chemical and isotopic clues. Imagining the coastlines of Vaalbara dotted with stromatolites gives a different sense of what that ancient continent was like. Instead of barren silence everywhere, there were pockets of quiet activity in shallow waters, low mounds rising just above the sediment, their surfaces coated with thin layers of living cells. The air above carried the faint tang of salt and volcanic gases, and the sound of waves moved steadily across the shore. Sunlight warmed the upper layers of water, and microbial communities carried out their slow work, dividing, growing, and releasing tiny amounts of oxygen that would react with minerals and settle to the sea floor. The pace was unhurried, measured not in days but in thousands of years, yet the direction of change was steady. Over time, the accumulation of oxygen in localized environments began to influence other organisms. Some microbes evolved ways to tolerate or even use oxygen, while others retreated to environments where it remained scarce. This gradual shift in chemistry set the stage for one of the most significant transitions in Earth's history. Though during the age of Valbara it was still only in its earliest phases, stromatolites also remind us that complexity does not always require size. A microbial mat, though only a few centimetres thick, can contain billions of individual cells belonging to many different species. Chemical gradients develop over distances smaller than the width of a fingernail, creating microenvironments where different metabolic processes occur side by side. The result is a level of ecological complexity that is easy to overlook but profound in its implications. The durability of stromatolites is another reason they are so valuable to scientists. While individual cells decay quickly, the mineral layers formed within stromatolites can survive burial, metamorphism, and even moderate heating. These structures provide some of the oldest direct evidence of life, allowing researchers to study the environments and processes that existed in the Archaean world. There is also something quietly poetic, though not in a dramatic sense, about the idea that life's earliest visible monuments were built not by animals or plants, but by microorganisms working together in shallow seas. These structures were not intentional creations, they were byproducts of survival, the accumulated result of countless ordinary days in the lives of microscopic organisms, and yet those ordinary days changed the planet. If you imagine standing on a rocky shoreline and watching the tide recede, revealing patches of layered stone, it is possible to picture those ancient stromatolites in their original setting, alive and growing, their surfaces glistening with moisture, their layers slowly thickening as sediments settled and cells multiplied. The sun would move across the sky, its light filtered through an atmosphere still lacking oxygen. The ocean would stretch outward, darker and richer in minerals than today's seas. And in the quiet shallows, life would continue its patient work, shaping the chemistry of the world in ways that would not become fully visible until far in the future. Understanding stromatolites helps us appreciate how gradual and interconnected the transformation of Earth has been. The oxygen produced by microbial mats, the minerals trapped in layered sediments, and the chemical reactions taking place in shallow waters were all part of a larger process, one that would eventually alter the atmosphere, influence climate, and create conditions suitable for more complex forms of life. Yet at the time, none of this was apparent. The changes were too slow, too subtle, unfolding over spans of time far beyond any individual lifespan, even the lifespan of entire species of microbes. The planet was changing, but it was changing quietly. At that distant time in Earth's history, even something as ordinary as a day was not quite what we would recognise now. The planet was spinning faster, and the cycle of light and darkness passed more quickly across the surface. Sunrise came sooner after sunset, and the night, though still deep and star-filled, did not last as long as the nights we experience today. For the world of Valbara, this slightly quicker rhythm shaped the environment in subtle but meaningful ways, influencing tides, temperatures, and the patterns of life in oceans that were still young. The reason for this faster rotation lies in the early relationship between Earth and the Moon. When the Moon first formed, likely after a colossal collision between the young Earth and a Mars-sized body, it orbited much closer than it does now. Gravity linked the two worlds in a powerful interaction. The Moon's pull raised tides in Earth's oceans, and as those tides moved, they created friction with the seafloor and coastlines. Over immense spans of time, this friction gradually slowed Earth's rotation, lengthening the day little by little. But 3 billion years ago, that slowing process was still underway. A day may have lasted only 18 hours, perhaps even a bit less in earlier periods. This meant that the sun crossed the sky more quickly, and the alternation between daylight and darkness occurred at a pace that would feel slightly hurried to us, though of course no one was there to notice the difference. It is interesting to consider how such a change in the length of the day affects a planet. Temperature, for example, is influenced by how long sunlight warms the surface, before night brings cooling. With shorter days, the surface may have had less time to heat up under direct sunlight, but also less time to cool during the night. The result was not necessarily a colder or warmer world overall, but one in which temperature fluctuations followed a different rhythm. In coastal regions, where shallow waters warmed quickly in sunlight and cooled just as quickly after sunset, these shorter cycles may have influenced the activity of microbial communities. Photosynthetic organisms depended on light, and the duration of daylight determined how long they could produce energy each cycle. A shorter day meant more frequent transitions between light and dark, perhaps encouraging adaptations that allowed microbes to respond quickly to changing conditions. The faster rotation of Earth also influenced the atmosphere. A spinning planet experiences the Coriolis effect, which shapes wind patterns and ocean currents. When rotation is faster, these effects become stronger, potentially altering the circulation of air and water on a global scale. While the exact patterns of Archaean winds are difficult to reconstruct, it is likely that storms, trade winds, and ocean currents followed somewhat different paths than they do today. Clouds drifting across the sky of Vaalbara may have formed and dissipated under these shifting winds, casting moving shadows across volcanic landscapes and shallow seas. Rainfall patterns, too, would have been shaped by atmospheric circulation, influenced by both the faster rotation and the arrangement of land and ocean. Another consequence of a closer moon and faster rotation was stronger tides. Tides are driven primarily by the gravitational pull of the moon, and when the moon is nearer, that pull is greater. In the Archaean, tidal ranges in some coastal areas may have been significantly larger than those we see today. Water advanced farther inland and retreated more dramatically, exposing broad tidal flats and then covering them again. These tidal cycles created environments that were constantly changing, sometimes submerged, sometimes exposed to air and sunlight. Such conditions were ideal for microbial mats and early photosynthetic organisms, which could thrive in shallow waters rich in nutrients. The mixing caused by tides also helped distribute minerals and oxygen locally, shaping the chemistry of coastal ecosystems. Standing on the shoreline of Volbara, if it had been possible, you might have noticed the tide rising more quickly than expected, the water moving steadily across dark rock, filling channels and pools that only hours earlier lay exposed. Later, the sea would withdraw again, leaving behind wet surfaces glistening under the shifting light of a shorter day. The night sky during this era would also have been different in subtle ways. The moon, appearing larger than it does now, would have dominated the darkness, its light reflecting across the ocean in bright shimmering paths. With little atmospheric pollution and few airborne particles produced by vegetation, the stars would have appeared sharp and numerous, scattered across a sky untouched by artificial light. Constellations, of course, were not yet the ones we know. The positions of stars change slowly over time as they move through the galaxy, and over billions of years those changes become significant. The night sky of the Archaean would have been familiar in its beauty, but unfamiliar in its details. Patterns of stars arranged differently, some brighter, some dimmer, all turning slowly overhead as the Earth rotated beneath them. Meteor showers may have been more frequent as well, remnants of the solar system's early debris occasionally entering the atmosphere and burning into streaks of light. Each meteor would have flashed briefly, leaving behind a fading trail, a reminder that the solar system itself was still settling into the quieter configuration we know today. The length of the year, on the other hand, was not dramatically different. Earth's orbit around the Sun has remained relatively stable over billions of years, so the number of days in a year was greater when days were shorter. In other words, a year during the time of Vaalbara contained more days than a modern year, even though the total time required for one orbit was much the same. This difference would have been meaningless to the microorganisms that dominated the biosphere, yet it illustrates how even fundamental aspects of timekeeping depend on planetary conditions that can change over geological history. Day and night also influenced chemical processes in the oceans. Sunlight drove photosynthesis in the upper layers of water, while darkness allowed other reactions to dominate. Temperature changes between day and night affected the solubility of gases and the movement of currents in shallow regions. These daily cycles, though shorter than today's, were part of the steady rhythm that shaped early ecosystems. Volcanic activity sometimes added its own glow to the darkness. Lava flows could remain hot for long periods, and eruptions occasionally illuminated the horizon with a dull red light. Steam rising from fissures or vents might have drifted through the air, visible in the cooler hours before dawn. The transition from night to day in such a world would have been gradual but striking. First, a faint glow on the horizon, filtered through an atmosphere rich in volcanic gases. Then the sun rising, its light scattering differently through the haze, casting long shadows across rocky terrain. The ocean surface catching the light, shifting in colour as the angle of illumination changed. With the sun higher, temperatures would rise, winds might strengthen, and microbial communities in shallow waters would resume photosynthesis, continuing the slow release of oxygen that was beginning to alter the planet's chemistry. Later, as the sun descended, the light would soften, the air cooling, the surface of the ocean darkening once again. Night would arrive sooner than we might expect, stars appearing one by one, and the moon climbing into the sky, bright and imposing. These cycles repeated endlessly, day after day, year after year, across spans of time so long that continents formed and broke apart while the rhythm of light and darkness continued unchanged in its basic pattern. It is easy to overlook how fundamental this rhythm is to life. Even today, circadian rhythms in living organisms reflect the cycle of day and night, influencing sleep, metabolism, and behaviour. In the Archaean, microbial life may have responded to similar cycles, adjusting metabolic processes according to the availability of light and the changing conditions of temperature and chemistry. The faster rotation of Earth also affected the distribution of heat across the planet. Stronger Coriolis forces may have led to more complex wind patterns, helping to transport heat from equatorial regions toward higher latitudes. This circulation played a role in maintaining a relatively stable climate despite the faint young sun. Another subtle effect of a shorter day lies in the interaction between the atmosphere and the oceans. Frequent heating and cooling cycles influence evaporation and condensation, contributing to cloud formation and rainfall. Over long periods, these processes shape landscapes, carving channels, transporting sediments, and feeding rivers that carry minerals into the sea. Thinking about these interactions can give a sense of how interconnected Earth systems have always been. The rotation of the planet influences winds and tides. Winds and tides influence climate and ocean chemistry. Climate and chemistry influence life, and life, in turn, gradually alters the atmosphere. All of these processes were already underway during the time of Valbara, forming a network of relationships that would continue to evolve over billions of years. If you imagine pausing for a moment on that ancient shoreline, watching the sun set over dark water, the air cooling as the sky deepens into shades of purple and black, there is a quiet sense of continuity. The same sun that warmed those seas still rises each morning. The same moon still shapes the tides, though it now orbits farther away. The same planet still turns, carrying oceans and continents through cycles of light and darkness that have persisted since the earliest chapters of Earth's history. Far above the restless oceans of that early world, a larger moon hung in the sky, closer, brighter, and far more influential than the one we see today. Its presence shaped the rhythm of the planet in ways that reached far beyond the glow of its reflected sunlight. During the time when Vaalbara existed, the gravitational partnership between Earth and the Moon affected tides, the length of the day, the stability of the planet's tilt, and even the long-term patterns of climate. It was not simply a distant companion in the night sky. It was an active participant in the shaping of the environment in which early life and the first continents were slowly emerging. To appreciate how different things were, it helps to imagine the Moon not at its current distance of about 384,000 kilometres, but significantly closer. Billions of years ago, the Moon orbited nearer to Earth, and because gravitational force increases with proximity, its pull on the oceans was stronger. Each day, the rising and falling of tides would have been more pronounced, especially in shallow coastal regions. Water surged farther inland, then withdrew more dramatically, exposing wide stretches of shoreline before returning again. These stronger tides were not merely larger versions of modern tides. They likely influenced the chemistry and circulation of coastal waters in profound ways. When tides move in and out over broad flats and shallow basins, they mix water layers, redistribute nutrients, and expose organisms to cycles of wetting and drying. For microbial communities living along the edges of Valbara, these cycles created environments rich in opportunity but also full of challenges. Conditions changed not just daily, but several times within each shorter day, requiring resilience and adaptability from the organisms that lived there. Picture a wide tidal flat on the margin of that ancient continent. The sea advances steadily, filling channels carved into volcanic rock, covering mats of microorganisms that have grown across the surface. Minerals dissolved in seawater spread through the mat, and sunlight filtering through shallow water allows photosynthesis to continue. Hours later, the tide retreats, leaving behind pools of warm water trapped in depressions, while other areas are exposed to the open air and the intense ultraviolet light of the Archaean sun. Then, as the cycle repeats, the sea returns, bringing with it fresh minerals and cooler water. Over countless generations, these tidal rhythms shaped the behaviour and evolution of early life. Some microbes adapted to survive periods of dryness or high salinity. Others specialised in particular layers of the mat, depending on how often they were submerged. The tides were not simply background motion. They were a central part of the environment, setting the tempo of daily existence. The Moon's influence extended beyond tides. Its gravitational interaction with Earth gradually slowed the planet's rotation, a process that continues even today. As tides move across the oceans, friction between water and the seafloor dissipates energy, and that energy ultimately comes from Earth's rotational motion. The result is a very gradual lengthening of the day and a slow increase in the distance between Earth and the Moon. During the age of Valbara, this process had already been underway for more than 1 billion years, but the day was still shorter than it is now. The Moon's pull, stronger then, meant that tidal forces were more energetic, and the transfer of rotational energy was occurring at a slightly faster rate. Over immense spans of time, this steady exchange would reshape the fundamental rhythm of the planet, stretching days from perhaps 18 hours toward the 24-hour cycle we experience now. Another effect of the Moon, less obvious but equally important, involves the tilt of Earth's axis. The angle at which Earth is tilted relative to its orbit determines the strength of seasons and the distribution of sunlight across the planet. Without the stabilizing influence of the Moon, that tilt could vary chaotically over millions of years, leading to extreme and unpredictable climate shifts. Mars, which lacks a large moon, provides an example of how such instability can occur. Earth, by contrast, has enjoyed remarkable stability in its axial tilt, and the moon is largely responsible. Even in the Archaean, this stabilization would have helped maintain relatively consistent patterns of climate over long periods, allowing oceans to remain liquid and providing conditions in which life could persist and evolve. Looking up at the moon from the surface of Vaalbara, its appearance would have been striking. Because it was closer, it would have appeared larger in the sky, its disk occupying more space above the horizon. The details of its surface, the broad dark plains and brighter highlands, would have been more pronounced to the naked eye. Moonlight reflecting off the oceans would have cast brighter paths across the water, illuminating waves and shorelines during the night. Night itself would have been a quiet time in many parts of that ancient world. Without artificial lights and with little oxygen to scatter light in the atmosphere, the stars would have shone with exceptional clarity. The Milky Way would have stretched across the sky as a luminous band, and the larger moon would have moved steadily along its orbit, rising and setting in a cycle that influenced the timing of tides and the behaviour of microbial communities in coastal waters. It is interesting to think about how different the relationship between land and sea might have looked under these conditions. Stronger tides can erode coastlines more quickly, reshaping bays and inlets, carving channels, and redistributing sediments. Over thousands of years, these processes can transform the outline of a shoreline, even in the absence of large storms or dramatic sea level changes. In the Archaean, where vegetation did not yet anchor soils and stabilise sediments, tidal erosion may have been particularly effective. Rocky coastlines were worn down, and sediments carried into shallow seas settled in layers that would eventually become part of the geological record. Each tidal cycle contributed a tiny increment to this process, and over millions of years, those increments added up to significant changes in the landscape. The moon also influenced the mixing of the oceans on a broader scale. Tidal forces do not only affect coastal regions, they generate internal waves and currents that help circulate water, distributing heat and nutrients. In a world where atmospheric circulation and ocean currents were already shaped by a faster rotation and different continental arrangements, these tidal effects added another layer of complexity to the planet's climate system. One can imagine warm equatorial waters moving gradually toward higher latitudes, driven by winds and currents, while tides stirred shallow seas along the margins of Vaalbara. The interaction of these processes helped prevent extreme temperature differences between regions, maintaining conditions in which liquid water remained widespread despite the sun's lower luminosity at that time. There is also a deeper sense in which the moon influenced the rhythm of the planet, not only physically, but temporally. The regular rise and fall of tides, the predictable cycle of lunar phases, and the steady slowing of Earth's rotation all contributed to a sense of order in a world that was otherwise geologically restless. Volcanoes erupted, continents shifted, and the chemistry of the atmosphere and oceans evolved. Yet the gravitational dance between Earth and Moon continued with quiet reliability. This predictability may have mattered for early life in ways we are only beginning to understand. Rhythmic environmental cycles, whether driven by tides, day and night, or seasonal variations, provide opportunities for organisms to adapt and synchronize their metabolic processes. Even simple microorganisms can respond to periodic changes in light, temperature, and nutrient availability, adjusting their activity in ways that improve survival. In tidal environments, for example, microbial mats may have developed internal rhythms tied to the cycle of submergence and exposure. Photosynthetic activity increased when sunlight was available, and water levels were favourable. Chemical processes dominated during darker or submerged phases. Over time, these repeated patterns shaped the structure and function of entire communities. The presence of the moon also had implications for the long-term evolution of Earth's interior. Tidal forces do not only act on oceans, they also exert stresses on the solid crust and mantle. While these stresses are small compared to those generated by plate tectonics, Over immense spans of time, they may have influenced patterns of faulting and volcanic activity in subtle ways. Thinking about all of this together, it becomes clear that the moon was not merely an ornament in the sky, but an integral part of Earth's system. Its gravity-shaped tides influenced rotation, stabilized climate, and contributed to the environmental rhythms that guided the development of early ecosystems. Imagining an evening on the shores of Vaalbara, the sun setting over a mineral-rich sea, the air cooling as the sky darkens, it is possible to picture the moon rising larger than we see it now. Its light reflects off the water, and the tide begins its steady advance, filling channels and pools carved into the rock. Microbial mats glisten under the returning water, and the slow work of life continues, generation after generation, guided in part by the gravitational pull of a companion world overhead. Hours later, the tide recedes again, leaving behind wet surfaces that steam slightly in the cooler night air. Stars fill the sky, and the Milky Way stretches from horizon to horizon. Somewhere in the distance, volcanic activity may cast a faint glow, a reminder that the planet beneath this tranquil scene is still releasing heat, still reshaping itself from within. These cycles repeat endlessly, tides rising and falling, days passing more quickly than they do now, the moon slowly drifting outward in its orbit, carrying with it a fraction of Earth's rotational energy. Over millions of years, these small changes accumulate, lengthening the day, altering the rhythm of tides, and gradually transforming the relationship between Earth and its satellite. What is striking is how these slow, almost imperceptible processes connect the distant past to the present. The tides we observe today are part of the same system that influenced the coastlines of Valbara. The moon that lights the night sky now is the same one that shone on those ancient seas, though it has moved farther away and appears slightly smaller than it once did. This continuity gives a sense of the immense span of time involved. The landscapes, the atmosphere, and the forms of life have changed almost beyond recognition, yet some of the fundamental rhythms of the planet remain, carried forward through billions of years. Long before forests softened the wind or grasslands slowed the movement of air across the land, weather on Earth operated in a world of bare rock, warm seas, and an atmosphere very different from the one we breathe now. The first supercontinent existed under skies shaped by volcanic gases, shifting cloud layers, and the steady circulation of heat between ocean and air. Storms formed, rain fell, winds moved across the surface, and climates developed, even though the landscapes beneath them would have looked stark and unfamiliar to modern eyes. To picture the climate of Vaalbara, it helps to begin with the broader conditions of the Archaean Earth. The sun, though already stable and shining steadily, produced slightly less energy than it does today. This difference, sometimes called the faint young sun paradox, presents an interesting question. If the sun was dimmer, why was the planet not frozen solid? The answer appears to lie in the atmosphere. Higher concentrations of greenhouse gases, particularly carbon dioxide and methane, trapped heat effectively, maintaining temperatures warm enough for liquid water to exist over much of the planet's surface. This warmer, greenhouse-rich atmosphere influenced the entire climate system. Oceans evaporated more readily, and water vapour, itself a powerful greenhouse gas, accumulated in the air. Clouds formed frequently, especially over warm seas, and rainfall may have been more intense in many regions. Without extensive vegetation to absorb or slow the movement of water, rain striking the land flowed quickly into rivers and channels, carrying minerals into the oceans. Storms were likely common, particularly over coastal areas and shallow seas where evaporation was strong. Warm air rising from the surface created towering cloud systems, and lightning may have been a frequent feature of these storms. Thunder rolled across landscapes where there were no trees to echo the sound, no animals to seek shelter, only wind sweeping across volcanic plains and waves breaking against rocky shores. The structure of storms in the Archaean may have differed somewhat from modern storms, because the atmosphere contained different gases and aerosols. Volcanic eruptions released fine particles into the air, and these particles acted as nuclei around which water droplets could form. This may have influenced cloud formation, potentially making clouds thicker or more widespread in some regions. Another factor shaping weather patterns was the faster rotation of the Earth. A more rapidly spinning planet experiences stronger Coriolis forces, which influence the paths of winds and storms. Air currents that might travel in relatively straight lines on a slower rotating world are deflected, creating circulating systems that distribute heat and moisture around the globe. These patterns would have shaped rainfall, temperature differences, and the movement of storm systems across Vaalbara. The arrangement of land and sea also played an important role. A supercontinent changes climate in ways that smaller land masses do not. Coastal regions tend to have more moderate temperatures, influenced by the nearby ocean, while interior regions can experience greater temperature swings. In the case of Vaalbara, the continent was probably smaller than later supercontinents, so vast desert interiors may not have been as extensive as those that formed during the time of Pangaea. Still, inland regions likely experienced different conditions from the coasts, with less humidity and fewer clouds. Temperature differences between land and sea drove winds, just as they do today. During the day, land surfaces warmed more quickly than the oceans, causing air to rise and drawing cooler air inland from the sea. At night, the pattern reversed as land cooled faster than water. These daily cycles created breezes that moved steadily across shorelines, shaping waves and influencing the distribution of heat and moisture. Rainfall patterns were probably uneven, influenced by geography, atmospheric circulation, and volcanic activity. Some regions may have experienced frequent heavy rains, especially near coastlines or areas of rising air currents. Other regions, particularly those shielded by topography or distant from sources of moisture, may have been relatively dry. Without plants to hold soil in place, erosion during heavy rains could be intense, water flowing across bare rock-carved channels quickly, carrying sediments into rivers and eventually into the oceans. Over time, these sediments accumulated in layers, preserving records of climate and weather patterns in ancient rock formations. Volcanoes also had a significant influence on climate. Large eruptions released gases and particles that could temporarily alter atmospheric conditions. Sulfur compounds, for example, can form aerosols that reflect sunlight, cooling the surface for periods that might last months or years. At the same time, carbon dioxide released by volcanic activity contributed to long-term warming. This balance between cooling and warming influences likely caused climate to fluctuate on various timescales, from short-term changes following eruptions to longer-term shifts driven by tectonic processes and changes in atmospheric composition. Another aspect of Archaean climate that is worth considering is the role of the oceans in storing and distributing heat. Water has a high heat capacity, meaning it can absorb and retain large amounts of energy without changing temperature rapidly. This property helps moderate climate, reducing extreme temperature swings between day and night or between seasons. Ocean currents, driven by winds and differences in temperature and salinity, transported heat around the planet. Although the exact patterns of Archaean ocean circulation are difficult to reconstruct, it is likely that these currents played a crucial role in maintaining relatively stable global temperatures despite the faint young sun. Cloud cover also influenced climate by reflecting some sunlight back into space while trapping heat beneath. The balance between these effects depends on cloud type, altitude, and coverage. In a world with abundant water vapor and volcanic aerosols, cloud patterns may have been extensive, contributing to a climate that was warm but not uniformly so. Seasonal changes during the time of Valbara would have been influenced by the tilt of Earth's axis, much as they are today. The moon's stabilizing effect helped maintain a relatively consistent axial tilt, preventing the extreme variations that might otherwise have occurred. As a result, seasonal cycles likely existed, though their intensity depended on latitude and local geography. In equatorial regions, seasonal differences may have been subtle, with temperatures remaining relatively stable year-round. Higher latitudes, however, would have experienced more pronounced changes in sunlight and temperature over the course of the year, though the warmer global climate of the Archaean may have reduced the likelihood of large ice sheets forming. It is interesting to imagine what a storm might have looked like on Vaalbara. Dark clouds gathering over a warm ocean, the air growing heavy and still before the first gusts of wind arrive. Rain beginning to fall, at first in scattered drops, then in sheets, striking bare rock and sending rivulets of water racing toward the sea. Lightning illuminating the landscape in brief flashes, thunder rolling across a shoreline where microbial mats cling to tidal flats. After the storm passes, the air clears, and the surface of the land glistens with moisture. Pools of water collect in depressions, evaporating slowly under the returning sunlight. Minerals dissolved in the rainwater leave faint deposits as they dry, adding to the chemical complexity of the environment. Over thousands of years, repeated cycles of rain, erosion and sedimentation gradually reshape the landscape. Channels deepen, basins fill, and layers of sediment accumulate, preserving records of ancient climates that scientists can study billions of years later. Another feature of Archaean weather may have been the frequency of fog and mist in coastal regions. Warm, humid air moving over cooler water or land can create thick fog, reducing visibility and blanketing the landscape in a quiet, muted atmosphere. Such conditions would have been common in areas where temperature differences between air and surface were pronounced. Wind patterns, too, shaped the environment in subtle ways. Strong winds could lift fine particles of ash or dust, carrying them across long distances before they settled again. These airborne sediments contributed to the layering of rocks and influenced the distribution of nutrients in both land and sea environments. All of these processes, rainfall, wind, storms, erosion and sedimentation, were already part of Earth's system during the time of the first supercontinent. The same physical principles that govern weather today were at work then, though under different atmospheric conditions and on landscapes that lack the stabilizing influence of vegetation. It is easy to think of climate as something static, but in reality it is always changing, influenced by countless interacting factors. During the Archaean, these factors included volcanic activity, atmospheric composition, ocean circulation, solar output, and the arrangement of continents. Each played a role in shaping the conditions experienced on the surface. The persistence of liquid water throughout this time is one of the most important clues we have about early climate. Sedimentary rocks formed in shallow marine environments, ripple marks preserved in ancient sandstones, and chemical signatures in minerals all point to the presence of oceans and an active hydrological cycle. These clues remind us that even in a world that would have seemed alien to modern eyes, the essential patterns of weather were already in place. Clouds formed, rain fell, winds blew, and storms passed, just as they do now. The difference lay in the details, the composition of the air, the absence of plants and animals, the stronger tides, and the higher heat flow from the planet's interior. Standing in imagination on the shore of Valbara, watching dark clouds gather over a mineral-rich sea, there is a sense of continuity. The same sun drives evaporation. The same gravity pulls rain toward the surface. The same laws of physics govern the movement of air and water, and as storms swept across that ancient continent and rains carved channels into volcanic rock, the environment in which early life existed continued to evolve. Weather and climate influenced the chemistry of oceans, the distribution of nutrients, and the conditions in which microorganisms lived and reproduced. Those microorganisms, in turn, were gradually altering the atmosphere itself, releasing oxygen in tiny amounts that would accumulate over immense spans of time. The interplay between climate geology and biology was already underway, setting the stage for transformations that would reshape the planet in ways that were only just beginning to unfold and that would eventually change not only the air and the oceans, but the very nature of life on Earth itself. Silence, at least the kind of silence we rarely experience today, would have been one of the most striking features of the Earth during the time of Vaalbara. Not absolute silence, because the planet was never truly quiet, but a different kind of soundscape, one shaped almost entirely by wind, water, and the restless movements of the ground itself. There were no bird calls at dawn, no insects humming in the air, no rustling leaves, no distant footsteps of animals moving across the land. The world had sound, but it was the sound of the planet rather than the sound of life as we know it. To imagine that environment, it helps to begin with the wind. Air moving across the surface of the Earth has always produced sound, and on a barren continent of exposed rock, the wind would have had little to interrupt or soften it. Today, forests and grasses absorb and scatter airflow, breaking it into countless smaller currents. In the Archaean, the land was largely bare, and the wind could travel across long stretches of terrain without obstruction, rising and falling over volcanic ridges, sweeping across plains of hardened lava, and carrying fine particles of dust and ash. The sound of such wind would not necessarily have been loud all the time, but it would have been constant in many regions, a low, steady movement of air across stone. During storms, that sound would intensify, gusts roaring across the landscape, perhaps whistling through cracks and fissures in cooling rock. Without trees or tall vegetation, there would be fewer sharp, fluttering sounds, and more deep, continuous tones shaped by the contours of the land itself. Near the coasts, another sound would have dominated: waves. Oceans during the time of Valbara were already vast, and waves driven by wind and tides rolled against rocky shorelines much as they do today. Yet even this familiar sound would have been subtly different. Sandy beaches were less common, and many coastlines were likely formed of volcanic rock or coarse sediments. Waves striking such surfaces produce sharper, more echoing sounds than waves breaking on soft sand. Stronger tides, caused by the moon's closer orbit, may also have contributed to a more pronounced rhythm along the shores. Water advancing and retreating over broad tidal flats would have created gentle surges, the quiet movement of shallow currents filling and draining channels carved into the rock. In sheltered areas, the sound might have been a soft lapping, while in more exposed regions the ocean could produce a steady, resonant crashing as waves met cliffs or hardened lava flows. Rain, too, would have added its voice to this ancient world. Storms were likely frequent in many regions, and when rain fell on bare stone, the sound was different from rain falling on soil or vegetation. Droplets striking rock create sharper, more distinct impacts, and when heavy rainfall pours across a landscape without plants to absorb it, water quickly gathers into streams, producing the sound of flowing channels that form and disappear within hours or days. Thunder would have rolled across open terrain, echoing off distant rock formations, travelling far without forest to dampen it. Lightning flashing across a hazy sky would have been followed by long rumbling echoes, the sound carrying across volcanic plains and shallow seas. Volcanic activity itself was another powerful contributor to the soundscape. Eruptions could be explosive or effusive, depending on the composition of the magma and the interaction with water. Explosive eruptions produced deep concussive booms, followed by the rumble of ash clouds and falling debris. Effusive eruptions, where lava flowed steadily rather than violently, generated quieter but still dramatic sounds. The crackling of cooling rock, the hiss of steam where molten lava met water, and the low roar of molten rivers moving slowly across the surface. These sounds were not constant everywhere, but in regions near active volcanic centres, they may have been part of the background of daily life, if life could be said to have daily experiences at all in a microbial world. Beneath the surface, the Earth was also making noise, though much of it would not have been audible to a human ear. Tectonic movement produces vibrations, some large enough to be felt as earthquakes, others too subtle to notice without instruments. When earthquakes did occur, they could send shock waves through the ground, causing rock to fracture, cliffs to collapse, and loose material to slide. The grinding and cracking of rock during such events would have added brief but dramatic sounds to an otherwise steady environment. In coastal waters, hydrothermal vents on the seafloor release jets of hot, mineral-rich water. These vents produce sounds even today, a faint roaring or crackling as superheated fluids mix with colder seawater. In the Archaean, with volcanic and tectonic activity more intense, such environments may have been widespread, creating underwater soundscapes filled with subtle currents, bubbling gases, and the shifting of mineral deposits. Of course, most of these underwater sounds would not have been heard above the surface, but they were part of the environment in which early life existed. Sound travels differently in water than in air, often carrying farther and more efficiently. Microorganisms themselves may not have perceived sound in the way animals do, but vibrations and pressure changes influence their environments, shaping currents and mixing nutrients. One of the most striking aspects of this ancient soundscape is not what was present, but what was absent. There were no voices, no calls, no footsteps. Oh, the complex acoustic environments created by animals interacting with one another did not yet exist. Even the simple chirping of insects, a sound so common today that we sometimes forget to notice it, would not appear for billions of years. This absence would have given the world a different emotional quality, if one can use such a word for a time before human perception. The sounds of wind, water, and rock tend to be steady and continuous, rather than sharp and varied. They rise and fall gradually, creating an atmosphere that might have felt calm in some moments and immense in others, emphasizing the scale of the landscape rather than the activity of living creatures. Fog drifting across a shoreline would have muffled sound further, creating periods when even the crash of waves seemed distant and softened. Nights, illuminated by a larger moon, might have been especially quiet, with only the steady movement of the sea and the occasional distant rumble of geological activity breaking the stillness. It is interesting to consider how such an environment might have influenced the evolution of life once animals eventually appeared. Sound is an important sense for many organisms, used for communication, navigation, and detecting predators. In a world that began in near silence, these abilities developed slowly, emerging only after complex life evolved hundreds of millions of years later. The early Earth, then, was a place where sound existed without listeners, at least in the sense we understand listening. The planet produced its own rhythms driven by wind patterns, ocean currents, volcanic eruptions, and the steady turning of the globe beneath the sky. Another subtle contributor to the soundscape was the movement of sediments. Rivers carrying minerals from volcanic highlands to the sea would have produced gentle, continuous sounds as water flowed over rock and gravel. In shallow marine environments, waves shifting sand and sediment created faint scraping and sliding noises, too soft to hear at a distance but constant in their presence. Even the atmosphere itself produced sounds that are easy to overlook. Changes in temperature and pressure cause air to move and mix, creating faint rustling or whispering noises as currents interact. Without the masking effect of biological sounds, these subtle atmospheric movements might have been more noticeable, forming part of the background of daily and nightly cycles. Meteor impacts, though less frequent than in the earliest history of the planet, still occurred from time to time. A large impact would have been an extraordinary event, producing a shock wave that travelled through the air and ground, followed by the sound of debris falling and the distant rumble of collapsing rock. Such events were rare on human timescales but more common in the Archaean, adding occasional dramatic episodes to an otherwise steady acoustic environment. If you imagine standing just for a moment on a high outcrop of Vaalbara, looking out over a dark ocean under a hazy sky, the sounds you would hear would be simple but profound. Wind moving steadily across the land, waves breaking in the distance, perhaps the faint hiss of steam rising from a geothermal vent nearby. Far away, a low rumble hinting at volcanic activity beyond the horizon. Then, As night falls, the wind might calm and the sea would settle into a slow, rhythmic motion. The moon, larger than it appears today, would cast pale light across the water, and the stars would shine with a clarity seldom seen now. In that quiet, the planet itself would feel immense, its movements measured not in moments but in ages. This kind of soundscape can be strangely calming to imagine, perhaps because it lacks the urgency and complexity of modern environments. There are no sudden alarms, no crowded layers of noise, only the steady processes of nature unfolding at their own pace. Nothing on Earth's surface remains unchanged forever, not even the oldest continents. Vaalbara, like every supercontinent that would follow it, did not endure indefinitely. The same forces that brought fragments of crust together gradually began to pull them apart again. This process was not sudden or dramatic in the sense of a single event. It unfolded slowly, across tens of millions of years, driven by heat rising from deep within the planet and by the steady motion of tectonic plates that never truly comes to rest. To understand why Valbara broke apart, it helps to return to the interior of the Earth, where the mantle continues its slow circulation. Heat generated during the planet's formation, along with the ongoing decay of radioactive elements, keeps the mantle in motion. Hotter material rises, cooler material sinks, and over immense spans of time these currents move the plates of the crust above them. When continents assemble into a single large landmass, this circulation does not stop. In fact, the presence of a supercontinent can change the pattern of heat flow beneath it. Thick continental crust acts like an insulating blanket, slowing the escape of heat from the mantle below. Over time, that trapped heat can cause the underlying mantle to become warmer and more buoyant, increasing the likelihood of upwellings that push against the base of the crust. These upwellings, sometimes called mantle plumes, can weaken the crust from below. As heat builds, the rock expands slightly, and stresses develop within the continental mass. Cracks begin to form, often starting as long, narrow rifts where the crust is stretched and thinned. At first, these rifts may be subtle, expressed as valleys or zones of volcanic activity. But if the stretching continues, magma rises into the fractures, solidifying and widening them further. Over millions of years, a rift can deepen and expand until it becomes a new ocean basin, separating pieces of the continent that were once joined. This process has happened many times in Earth's history. The breakup of Pangaea, for example, began with rifting that eventually opened the Atlantic Ocean. Although the details of Vaalbara's breakup are more difficult to reconstruct, the same general principles apply. Heat accumulated beneath the supercontinent, stresses built within the crust, and eventually the landmass began to fragment. Another factor that may have contributed to the breakup is the motion of surrounding plates. Continents do not drift randomly. They are carried by tectonic plates that interact with neighbouring plates in complex ways. Subduction zones, where one plate sinks beneath another, can pull continents toward them, while spreading centres, where new crust forms, push plates apart. The balance of these forces changes over time, influencing the direction and speed of continental movement. In the Archaean, plate tectonics may not have operated in exactly the same way it does today. The mantle was hotter and the crust thinner in many regions. Some scientists suggest that tectonic plates moved more quickly, while others propose that plate boundaries were less well defined. Regardless of the details, the evidence preserved in ancient rocks indicates that large-scale crustal movements were already taking place. The breakup of Valbara would not have been visible in a single human lifetime, even if humans had existed then. The opening of a rift might progress only a few millimeters or centimeters each year, far too slowly to notice directly. Yet over millions of years that motion adds up, gradually transforming the shape of continents and oceans. Volcanic activity often accompanies rifting. As the crust stretches and thins, pressure on the underlying mantle decreases, allowing magma to form and rise. Lava flows spread across the surface, and volcanic gases are released into the atmosphere. These eruptions can cover large areas, leaving behind thick layers of basalt that mark the early stages of continental breakup. In some cases, rifting may stall, forming a failed rift that never develops into an ocean. In others, the process continues, and seawater eventually floods the widening gap, creating a narrow sea that expands into a full ocean basin over tens of millions of years. For Valbara, much of the direct evidence of these events has been lost, but geological clues suggest that its fragments gradually separated, becoming parts of different cratons that now lie far apart. The Kapval Craton in southern Africa and the Pilbara Craton in Australia, once likely neighbours, are now separated by thousands of kilometres of ocean, carried to their present positions by the slow drift of tectonic plates over billions of years. This gradual dispersal is a reminder that continents are not permanent features but temporary arrangements of crust. They assemble, persist for a time, and eventually break apart, only to be reassembled in new configurations later. This cycle of assembly and breakup is repeated many times, shaping the long-term evolution of Earth's surface. The breakup of a supercontinent also has significant effects on climate and the environment. When a large landmass fragments, new coastlines are created, increasing the area where land and sea interact. Shallow seas may form along the edges of the separating continents, providing new habitats for marine life and influencing ocean circulation. Ocean currents change as new passages open between land masses, altering the distribution of heat around the planet. Atmospheric circulation shifts as well, responding to new patterns of temperature and pressure. Over time, these changes can lead to long-term shifts in climate, affecting both the oceans and the atmosphere. During the Archaean, life was still dominated by microorganisms, so the ecological consequences of continental breakup were different from those in later eras. Yet even microbial communities were influenced by changes in coastal environments, water chemistry, and nutrient distribution. New shallow seas provided habitats where stromatolites and other microbial structures could flourish, while volcanic activity associated with rifting released minerals that supported biological processes. Another important consequence of continental breakup is the recycling of crust. As plates move and interact, some crust is subducted and melted, while new crust forms at spreading centres. This continual renewal of the surface plays a role in regulating the composition of the atmosphere and oceans over geological time, helping maintain conditions that allow liquid water and life to persist. Thinking about the breakup of Vaalbara can give a sense of how dynamic the Earth has always been. Even the earliest continents were not stable forever. They were shaped by forces deep within the planet, forces that operate on timescales far longer than human experience, but are nonetheless steady and persistent. Imagine standing, in thought, on a rocky plateau of that ancient continent. The landscape appears solid and unmoving. Mountains stand in the distance, and rivers carve their paths toward the sea. Nothing seems to change from one day to the next, yet far below the mantle is slowly flowing, heat is rising, and stresses are building within the crust. The process of breakup has already begun, though it will take millions of years before its effects become visible at the surface. Cracks widen imperceptibly. Magma intrudes into fractures and cools, strengthening some areas while weakening others. Over vast spans of time, the land begins to separate, the first stages of a transformation that will eventually scatter the fragments of Valbara across the globe. What makes this story especially compelling is that the processes responsible for that breakup are still at work today. Continents continue to move, though slowly. The Atlantic Ocean continues to widen as North and South America drift away from Europe and Africa. New crust forms along mid-ocean ridges, while old crust sinks back into the mantle at subduction zones. The Earth is not a static world, but a dynamic system, always changing, always reshaping its surface. The breakup of Valbara was one chapter in that ongoing story, an early example of the supercontinent cycle that would repeat again and again. Long after Vaalbara itself had begun to fragment and drift apart, its influence did not end. The disappearance of that first supercontinent was not a conclusion, but a transition, a quiet turning point in the long history of the planet. The processes that shaped Vaalbara, the formation of stable continental crust, the interaction between land, ocean and atmosphere, and the slow work of early life, all set conditions that would shape everything that followed. One of the most important ways Vaalbara influenced the future lay in the stabilization of continental crust. Before large, durable landmasses existed, much of Earth's surface was more easily recycled back into the mantle. Thin crust formed and was destroyed relatively quickly, leaving fewer long-lived environments where sediments could accumulate and where life could persist over extended periods. The assembly of larger continental blocks marked a shift. Thick, buoyant crust resisted subduction more effectively, allowing ancient rocks, sediments and microbial ecosystems to remain in place for immense spans of time. This stability mattered for life, even if life at that time consisted only of microorganisms. Stable shallow seas along continental margins provided environments where microbial mats could grow undisturbed for long periods. Sediments accumulated in layers, preserving chemical records of biological activity. Nutrients delivered by rivers and volcanic activity supported ecosystems that slowly expanded and diversified. Over millions of years, these environments became more complex, not in the sense of large organisms appearing yet, but in the variety of microbial communities and metabolic processes taking place. Different species specialized in different chemical pathways, some using sunlight, others using chemical reactions involving sulfur, iron, or methane. These interactions gradually altered the chemistry of oceans and atmosphere in ways that would eventually allow more complex life to evolve. Another consequence of early continental formation was the increased weathering of rocks on land. When rain falls on exposed rock, it dissolves minerals and carries them into rivers and oceans. This process, known as chemical weathering, plays a significant role in regulating atmospheric carbon dioxide over long timescales. Carbon dioxide dissolves in rainwater, reacts with minerals, and becomes locked into sediments that may remain buried for millions of years. During the Archaean, weathering rates may have been different from today because there were no plants to accelerate the breakdown of rock. Still, the presence of larger land masses meant more surface area exposed to rain and rivers, increasing the transport of minerals into the oceans. These minerals influenced ocean chemistry, providing nutrients for microbial life and affecting the balance of gases in the atmosphere. The slow accumulation of oxygen, one of the most important developments in Earth's history, was also connected to these processes. Cyanobacteria living in shallow seas released oxygen as a byproduct of photosynthesis. At first, most of that oxygen reacted with dissolved iron and other elements, but over time, as those sinks became saturated, oxygen began to accumulate in the atmosphere. This transformation did not occur during the lifetime of Valbara itself, but the conditions that made it possible were already in place. Stable continental margins, nutrient-rich coastal waters, and expanding microbial ecosystems all contributed to the gradual increase in oxygen that would eventually lead to the Great Oxidation event hundreds of millions of years later. The influence of Vaalbara extended beyond biology and chemistry into the realm of tectonics. The formation of one supercontinent demonstrated that large-scale continental assembly was possible. Once the processes of plate motion, collision and stabilization had operated long enough to create one large landmass, they continued to operate, shaping the future of the planet's surface. Over the next billions of years, continents would assemble and break apart repeatedly. Rodinia, Pannotia, and later Pangaea were all part of this supercontinent cycle. Each cycle influenced climate, sea level, ocean circulation, and the distribution of habitats for living organisms. In this sense, Valbara was the first expression of a pattern that would repeat again and again, a rhythm in which the surface of the Earth reorganized itself on timescales far longer than any human history. It is interesting to think about how different Earth might be today if stable continental crust had never formed in those early eras. Without continents, weathering rates would be lower, nutrient delivery to the oceans would differ, and the chemical balance of the atmospheres might never have shifted in the same way. Life might still exist, but it would likely be very different, perhaps remaining confined to microbial ecosystems in the oceans, without ever giving rise to complex organisms on land. In this way, the emergence of early continents, including Vaalbara, can be seen as one of the key steps in making Earth the kind of planet it is today. Another aspect of Vaalbara's legacy lies in the rocks themselves. Some of the oldest Cratons that formed during or before its existence still survive as the cause of modern continents. These ancient fragments have endured collisions, mountain building, erosion, and countless other changes, yet they remain part of the continents we see on maps today. Walking across certain regions of South Africa or Western Australia, for example, you may be standing on rocks that formed when the first supercontinent existed. The landscapes above them have changed many times, but the foundations remain, carrying within them a record of conditions that existed billions of years ago. These ancient rocks also hold valuable clues about the early Earth. They preserve information about volcanic activity, ocean chemistry, atmospheric composition, and the presence of early life. Without them, our understanding of the Archaean world would be far more limited. The breakup of Valbara also contributed to the diversification of environments. When a supercontinent fragments, new coastlines form, and shallow seas spread across continental margins. These environments are often rich in nutrients and sunlight, making them ideal habitats for photosynthetic organisms. The expansion of such habitats may have supported the growth and spread of microbial communities, increasing biological productivity and accelerating changes in atmospheric composition. At the same time, the opening of new ocean basins altered circulation patterns, affecting climate and the distribution of heat around the planet. These changes, though gradual, influenced the conditions in which life evolved, creating new opportunities for adaptation and diversification. Over immense spans of time, the combined effects of tectonics, climate and biology transformed the planet. Oxygen levels rose, complex cells evolved, and eventually multicellular organisms appeared. Forests spread across continents, animals moved onto land, and ecosystems became increasingly intricate. All of these developments were still far in the future during the age of Vaalbara, yet the foundations were already being laid. The interactions between rock, water, air, and life that began in the Archaean continued without interruption, gradually reshaping the planet. It can be calming in a way to reflect on how slowly these transformations occurred. No single generation of microorganisms witnessed the full change in atmospheric composition. No single continent remained in one place for more than a fraction of geological time. The planet changed through countless small steps, each one almost imperceptible on its own, yet together forming a story that spans billions of years. Imagining the fragments of Vaalbara drifting apart across ancient oceans gives a sense of this slow movement. What had once been a single landmass became separate pieces, carried by tectonic plates that moved only centimetres each year. Over millions of years, those fragments travelled vast distances, eventually becoming parts of continents that would participate in later cycles of assembly and breakup. Meanwhile, life continued its quiet work. Microbial mats grew and spread. Oxygen accumulated slowly in certain environments. Chemical cycles operated in oceans and atmosphere, gradually shifting the balance of gases and minerals. There is a continuity in this story that connects the distant past to the present. The air we breathe, rich in oxygen, is the result of processes that began in those early oceans. The continents we inhabit are built in part from fragments of crust that formed billions of years ago. Even the patterns of plate tectonics that shape earthquakes and mountain ranges today are part of the same system that assembled and broke apart the first supercontinent. Thinking about this long chain of events can give a sense of perspective. The world we know is not a finished product, but a moment in an ongoing process, one that began long before the first supercontinent and will continue long after the present era. If you imagine standing once more on the shoreline of that ancient world, watching waves move across dark water beneath a hazy sky, it becomes easier to see how small beginnings can lead to vast outcomes. Tiny organisms, invisible to the eye, were altering the chemistry of the planet. Small fragments of crust were colliding and merging, forming the first continents. Heat rising from deep within the Earth was driving slow but powerful movements that would reshape the surface again and again. The future of life and continents was not determined in a single moment, but in countless quiet processes unfolding over immense spans of time. Right now, wherever you're sitting or lying, the ground beneath you feels steady and familiar. Floors, soil, pavement, stone, all of it seems fixed, as though the world has always been arranged exactly this way. Continents appear permanent on maps, oceans seem eternal, and the sky above feels like a constant presence that has never truly changed. Yet the story we have been drifting through reveals something quieter and far more expansive. Everything around you belongs to a planet that has been changing slowly and patiently for billions of years. It can be calming to pause and let that idea settle for a moment. The air you breathe carries oxygen that was not always there. The continents beneath your feet are built from fragments of crust that have assembled, broken apart, and assembled again in cycles so long that human history occupies only the briefest instant at the very end. The oceans have risen and fallen, changed their chemistry, and hosted life in forms that would seem strange and unfamiliar to us now. And far back in that deep past, long before forests, animals, or even the blue colour of the sky existed as we know it, there was a world where the first supercontinent formed, where microbial life lived quietly in shallow seas, and where tides moved across coastlines shaped by volcanic rock. Thinking about that ancient world does not require effort so much as patience. Deep time is not something to rush through. It unfolds slowly in the imagination, just as it unfolded slowly in reality, layer upon layer, change upon change, each step almost imperceptible on its own. You might imagine standing on a quiet shoreline, not of the modern world, but of that distant past. The air is warm, the sky slightly hazy, the ocean darker than the seas we know. Waves move steadily, and the sound of wind and water fills the space where birdsong and human voices would one day exist. The land is bare, shaped by heat and erosion, yet life is already present in forms too small to see, carrying out the slow work that will one day transform the planet. Now let that image fade gently, and return your attention to the present. The room around you, the sounds of modern life, the distant hum of electricity or the quiet of the night, all of it belongs to a moment in a story still unfolding. The Earth has not stopped changing. Continents continue to drift, oceans continue to circulate, and the atmosphere continues to evolve, though the changes now are often influenced by the presence of a species that has learned to observe and measure its world. There is something grounding about recognizing how small our own span of time is compared to the age of the planet. A human life, even a long one, is a brief flicker in geological terms, yet that does not make it insignificant. It simply places it within a larger context, a reminder that we are part of a story much older than ourselves. Sometimes, when the pace of daily life feels hurried, it can help to remember that the Earth moves at a different rhythm. Mountains rise and erode over millions of years. Oceans open and close over hundreds of millions. Even the rotation of the planet slows so gradually that centuries pass without anyone noticing the difference. This slower rhythm has a way of putting things into perspective. Imagine again the fragments of Vaalbara drifting apart, carried by tectonic plates moving no faster than your fingernails grow. No observer watching for a single day or even a lifetime would have seen the change. Yet over immense spans of time, those fragments travelled across the globe, eventually forming parts of continents that exist today. In a similar way, many of the changes in our own lives happen gradually, often unnoticed at first, becoming clear only when we look back after months or years. The planet itself teaches patience, showing that profound transformations rarely happen all at once. Another thought worth lingering on is how connected everything is. The heat rising from deep within the Earth drives the motion of plates. That motion shapes continents and oceans. Continents influence climate and ocean circulation. Climate affects the chemistry of the atmosphere and the distribution of life. Life in turn alters the atmosphere, which then changes the conditions for future life. This chain of interactions has been unfolding since the earliest days of the planet, linking the deep interior to the surface, the oceans to the air, the smallest microorganisms to the global environment. Even now, as you listen, those processes continue. Far beneath the surface, mantle currents move slowly, carrying heat upward. Along mid-ocean ridges, new crust forms, while in other regions, old crust sinks back into the mantle. The moon still raises tides, though it is farther away than it once was, and the length of the day continues to increase by a tiny fraction of a second each century. None of these changes are noticeable in daily life, yet they are always happening, quietly shaping the future. It can be strangely comforting to realise that the world does not depend on constant attention or effort to keep turning. The planet has its own momentum, its own steady pace, carrying oceans, continents and skies through cycles that began long before humans existed and will continue long after. Perhaps that is one of the reasons stories about deep time feel so soothing. They remind us that not everything moves quickly, that there is a vast background of slow, patient processes underlying the faster rhythms of modern life. If you let your thoughts drift once more, you might picture the night sky as it would have appeared billions of years ago. The moon larger, the stars brilliant in an atmosphere free of artificial light, the surface of the ocean reflecting pale light as tides move steadily along a quiet shore. Microbial life, unseen, continuing its work generation after generation, unaware that its small actions would one day change the entire planet, then gradually let that ancient sky blend into the present one. The same moon still rises, though smaller in the sky than it once was. The same stars still shine, though their patterns have shifted slowly over time. The same planet still turns, carrying us through cycles of day and night that began billions of years ago. There is a continuity here that stretches across all of Earth's history, a thread connecting the earliest oceans to the modern world, the first continents to the landscapes we know today. Standing in the present while thinking in deep time creates a quiet kind of perspective. It does not diminish the importance of the present moment. Rather, it gives that moment depth, placing it within a story so vast that every instant becomes part of something larger. You are here now, on a planet that has endured collisions, eruptions, ice ages and transformations beyond easy imagination. The ground beneath you may contain minerals that crystallized in ancient oceans, atoms that were once part of volcanic gases, elements forged in stars long before the Earth itself existed. And yet, despite all that history, the present moment is calm and immediate. Your breathing is steady. The world around you, whatever it contains, is quiet enough for reflection. There is no need to rush through these thoughts. Let them move at the same slow pace as the processes we have been exploring. Let the idea of deep time stretch gently in your mind, like a horizon that keeps extending the longer you look at it. Somewhere, far out in the oceans, waves are moving across the surface of water that has been part of this planet's cycle for billions of years. Somewhere, beneath the crust, heat is rising from the mantle, continuing the slow motion that shapes continents. Somewhere, tiny organisms are living in environments not so different from those of the Archaean, in hydrothermal vents or saline lagoons, continuing forms of life that have persisted almost unchanged for immense spans of time. The Earth carries its past within it, not as a distant memory, but as an active presence in every rock, every ocean current, every breath of air. And as you rest here thinking about a world that existed more than 3 billion years ago, there is a quiet realization that the story is not really about a vanished continent at all. It is about continuity, about how the present grows out of the past, and how even the smallest changes repeated over and over can reshape an entire planet. The same slow processes are still unfolding. Continents will continue to drift. Oceans will change. New supercontinents may form in the distant future, only to break apart again, repeating a cycle that began long before humans ever walked the Earth. But all of that lies far ahead, in times so distant that they feel almost abstract, just as the age of Vaalbara once seemed before we began to explore it together. For now, there is only this moment, this quiet stretch of time, this gentle awareness of the planet beneath you and the vast history it carries. Let that awareness settle, like sediment slowly sinking through still water, layer by layer, until everything becomes calm and unhurried, and the sense of deep time lingers softly in the background, like the steady motion of tides that continue, always, whether we notice them or not, or